somewhere in the direction of the Centaurus and Norma constellations, there's something massive pulling our entire galaxy toward it at 600 kilometers per second. We call it the Great Attractor, and despite decades of trying, we still can't see what it actually is. This gravitational anomaly affects hundreds of thousands of galaxies across hundreds of millions of light years, creating one of the largest structures we know about in the universe. The Great Attractor sits about 250 million light years away from us, in what astronomers call the zone of avoidance. This is the region of sky blocked by our own Milky Way's disk. Dust, gas, and billions of stars in our galaxy create a wall that obscures our view. It's like trying to see what's on the other side of a forest while standing in the middle of it. The very galaxy that gives us life also blinds us to one of the universe's biggest mysteries. What we do know comes from studying the motion of galaxies around us. In the 1970s, astronomers noticed something odd about cosmic movements. Galaxies weren't just flying apart from the Big Bang, they were also streaming in a particular direction. The Milky Way, along with our local group of galaxies, moves through space at about 630 kilometers relative to the cosmic microwave background radiation. When scientists calculated what gravity would be needed to cause this motion, they realized something enormous must be out there. The mass required is staggering. Estimates suggest the Great Attractor contains the equivalent of tens of thousands of galaxies worth of material. That's quadrillions of times the mass of our Sun concentrated in one region. But here's what makes it strange. When we use radio waves and infrared light to peer through the dust, we don't see enough galaxies to account for all that mass. There's definitely a large supercluster of galaxies there called the Norma cluster, but it's not nearly massive enough to explain the pull. Some scientists think the Great Attractor might not be a single object, but a dense region where multiple galaxy clusters overlap. The gravitational effects would add up, creating the appearance of one massive attractor. Others propose that dark matter might be concentrated there in unusual amounts. Since we can't see dark matter directly, this would explain why the region seems undermassive when we count visible galaxies. X-ray observations have revealed some of what lies hidden behind our galaxy's disk. Hot gas between galaxy clusters glows in X-rays, and these observations show a complex web of material in the Great Attractor's direction. But even these advanced techniques can't fully map what's there. We're essentially trying to understand the shape of something by looking at its shadow. The mystery deepened when astronomers discovered that the Great Attractor itself is moving. It's being pulled by something even larger called the Shapley supercluster, which lies beyond it. This suggests we're seeing just one part of an enormous cosmic flow where matter streams along vast gravitational rivers. The universe appears to have a large-scale structure that we're only beginning to understand. In the constellation Eridanus, there's a patch of space that's disturbingly empty. The CMB cold spot, as astronomers call it, is a void so large that it challenges our understanding of how the universe formed. Spanning 1.8 billion light-years across, it contains far fewer galaxies than any region of space this size should have. According to our current models of cosmic evolution, it simply shouldn't exist. The discovery came from mapping the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. This ancient light is remarkably uniform, varying by only about 1 part in 100,000. But in 2004, scientists found a region that was significantly colder than its surroundings. The temperature difference is tiny, only about 70 millionths of a degree, but in the smooth CMB, this stands out like a mountain on a plane. At first, astronomers thought it might be a measurement error or a quirk in the data, but repeated observations confirmed it was real. The cold spot appears in multiple surveys using different instruments. When scientists looked deeper, they found that this cold region corresponds to an enormous cosmic void, a region with far fewer galaxies than normal. It's not completely empty, but it contains about 10,000 fewer galaxies than a typical region of the same size. The problem is that voids this large shouldn't have had time to form. In the standard model of cosmology, Matter in the early universe was distributed fairly evenly. Gravity gradually pulled matter together into the cosmic web we see today, creating clusters and filaments of galaxies separated by voids. But this process takes time. Computer simulations suggest that a void as large as the CMB cold spot would need longer than the current age of the universe to form through normal gravitational evolution. One explanation involves the integrated Sachs-Wolf effect. When light from the CMB passes through a large void, it loses energy climbing out of the gravitational well. In an expanding universe, the void grows while the light is passing through, making the well shallower by the time the light needs to climb out. This means the light loses more energy going in than it gains coming out, arriving at Earth slightly cooler. But calculations show this effect isn't strong enough to fully explain the observed temperature drop. Some physicists have proposed more exotic explanations. The void might be evidence of quantum entanglement between our universe and another universe in a multiverse. In this scenario, the cold spot would be a kind of bruise where another universe bumped into ours in higher dimensions. Others suggest it could be a texture, a defect in space-time left over from the early universe, like a knot in the fabric of reality. Another possibility is that the void is a supervoid containing smaller voids arranged in a way that amplifies the cooling effect. This nested structure could create a larger temperature drop than a single uniform void. Recent surveys have found evidence for this kind of structure, but it still doesn't fully account for the anomaly's size and depth. The cold spot remains one of the most studied anomalies in cosmology, because it might be telling us something fundamental about the universe that we don't yet understand. In 2012, astronomers discovered something that shouldn't exist according to traditional planetary formation theories. A planet wandering through space completely alone, racing through the darkness at 80,000 kilometers per hour with no star to call home. PSO J318.522 is a rogue planet, and it's changing how we think about what planets are and how they form. This cosmic orphan is about 80 light-years from Earth, practically in our backyard by astronomical standards. It has about 6 times the mass of Jupiter, but is still young, only 12 million years old. That youth is what allowed astronomers to spot it. Young planets still glow from the heat of their formation, and PSO J318.522 shines faintly in infrared light even without a star to warm it. Its surface temperature is about 1160 Kelvin, hot enough to melt silver. What makes rogue planets particularly strange is that they challenge our basic understanding of planet formation. The traditional model says planets form from the leftover disk of gas and dust around a new star. They should be gravitationally bound to their parent star forever. But PSO J318.522 has no star and shows no signs it ever had one. It's moving through space as part of a young stellar group called the Beta Pictoris moving group, but it's not orbiting any of the stars there. There are 2 main theories for how rogue planets form. The first is that they start life normally, forming around a star, but then get ejected through gravitational interactions with other planets or passing stars. Computer simulations show this happens more often than we might think. In systems with multiple large planets, gravitational tugs of war can fling one planet out into interstellar space. The second theory is more radical. Some rogue planets might form like stars do, directly from the collapse of a gas cloud, but without enough mass to ignite nuclear fusion. PSO J318.522 seems to support the second theory. Its properties are almost identical to the giant planets found around young stars, but there's no evidence it was ever in a planetary system. It appears to have formed in isolation, making it more like a failed star than an ejected planet. This blurs the line between planets and brown dwarfs, objects too small to be stars but too large to be typical planets. The discovery has profound implications for how common planets might be in the universe. If planets can form without stars, there could be billions or even trillions of rogue planets wandering the galaxy. Some estimates suggest there might be more rogue planets than stars, They're just incredibly hard to detect because they don't shine by reflected starlight like normal planets do. These lonely worlds might not be as barren as they seem. Larger rogue planets could retain thick atmospheres that trap heat from radioactive decay in their cores. Some might even have subsurface oceans kept liquid by internal heat. While life as we know it seems unlikely without a star's energy, these planets could potentially harbour exotic forms of life adapted to eternal darkness and cold. Studying PSO J318.5022 is easier than studying planets around stars because there's no bright stellar glare to block out. Astronomers have been able to study its atmosphere directly, detecting signs of thick clouds and weather patterns. It rotates once every 8.6 hours, creating powerful winds and storms in its atmosphere. The planet glows with its own heat in various shades of magenta and orange in infrared light. In 2012, astronomers discovered something that made them question basic physics: a galaxy shaped like a rectangle. LIDA 074886, located 70 million light-years away, looks like a cosmic emerald-cut gemstone floating in space. While galaxies come in spirals, ellipses and irregular shapes, finding one that's rectangular is like finding a naturally occurring cube in nature. It simply shouldn't happen. Galaxies form their shapes through gravity, rotation and collisions. Gravity pulls equally in all directions, creating spheres. Rotation flattens these spheres into disks. Collisions can distort galaxies into irregular shapes. But none of these processes should create right angles and straight edges. LIDA 074886 has both, with clearly defined corners that give it an unmistakably rectangular appearance when viewed from Earth. The galaxy spans about 50,000 light-years across, making it somewhat smaller than our Milky Way. But its shape is so unusual that astronomers initially thought it was an error in their observations. Multiple telescopes confirmed the same thing. This galaxy really does have a rectangular profile, with a length-to-width ratio of about 3:1. It's like someone took a normal elliptical galaxy and stretched it into a box shape. What makes this even stranger is that LIDA 074886 is not young. The stars within it are mostly old and red, suggesting the galaxy has maintained this bizarre shape for billions of years. Young galaxies can temporarily have odd shapes due to recent collisions or interactions, but old galaxies should have settled into more natural forms by now. Gravity should have smoothed out any corners long ago. The leading theory involves an incredibly rare type of galaxy collision. Computer simulations suggest that if two disk galaxies merge at exactly the right angle and speed, they can create a rectangular shape that persists for several billion years. The collision has to be perfectly edge-on, with the galaxies moving at specific velocities. Even a slight deviation would create an irregular blob instead of a rectangle. The odds of this happening are astronomically small. Inside LIDA 07486, stars orbit in complex patterns that maintain the rectangular shape. Most stars follow box-like orbits rather than the circular or elliptical orbits seen in normal galaxies. These orbits create a kind of traffic pattern where stars pile up at the edges, reinforcing the rectangular appearance. It's a delicate balance. If the orbital patterns were disrupted, the galaxy would quickly collapse into a more conventional shape. The galaxy also contains an unusual amount of dark matter distributed in a ring around its edges. This dark matter halo might act like an invisible frame, helping to maintain the rectangular shape against the inward pull of gravity. Some astronomers suggest this dark matter distribution is key to the galaxy's stability, though how it formed this way remains a mystery. Spectroscopic analysis reveals that LIDA 074886 is actually rotating, but not like a normal galaxy. Instead of spinning like a disk or tumbling like a football, it rotates end over end like a cosmic brick. This rotation is slow, taking about 1 billion years to complete one turn. The rotation might help maintain the shape by creating centrifugal forces that counteract gravity at the corners. LIDA 074886 has forced astronomers to reconsider what shapes are possible for galaxies. It demonstrates that under extremely rare circumstances, the universe can create geometric forms that seem to violate our intuition about how gravity works. KIC 8462852, better known as Tabby's star, is doing something that has astronomers completely baffled. This otherwise ordinary star, 1,470 light-years away in the constellation Cygnus, randomly dims by up to 22%, and we have no idea why. When planets pass in front of stars, they typically cause dips of less than 1%. Whatever is blocking Tabby's star is enormous, irregular, and unlike anything we've seen before. The mystery began in 2015 when astronomer Tabitha Boyajian noticed strange patterns in data from the Kepler Space Telescope. Kepler monitored the brightness of over 150,000 stars, looking for the regular dips caused by orbiting planets. But Tabby's star showed dips that were neither regular nor planet-like. Some lasted for days, others for weeks. The depth varied wildly, sometimes 5%, sometimes 15%, and once an incredible 22% of the star's light was blocked. What makes this even stranger is that the dimming is completely aperiodic. There's no pattern, no predictable cycle. The star can shine normally for hundreds of days, then suddenly start dimming. The shape of the light curves, how brightness changes over time, is also bizarre. Planet transits create smooth, U-shaped dips. Tabby's star shows jagged, complex patterns with multiple dips overlapping, as if many objects of different sizes were passing in front of it simultaneously. Initial theories focused on natural explanations. Maybe a swarm of comets was breaking apart near the star, creating clouds of dust. But calculations showed you'd need 648,000 comets, each 200 kilometres wide, to create the observed dimming. That's an impossibly large number, and comets would create infrared emissions that weren't detected. A planetary collision could create debris, but that would also produce infrared excess that's missing. The lack of infrared excess is crucial. When dust absorbs starlight, it heats up and re-emits that energy as infrared radiation. Tabby's star shows no such excess, meaning whatever is blocking the light isn't warming up like normal matter should. This rules out most conventional explanations involving dust, asteroids, or planetary debris. The blocking material seems to be either incredibly cold or somehow not absorbing the light it blocks. Some astronomers proposed more exotic explanations. Could it be a Dyson sphere, a hypothetical megastructure built by an advanced civilization to harvest energy from their star? This idea captured public imagination, but most scientists remain skeptical. SETI researchers pointed radio telescopes at Tabby's star, but detected no artificial signals. Still, the possibility hasn't been completely ruled out. Long-term observations revealed another layer to the mystery. By examining photographic plates dating back to 1890, astronomers discovered that Tabby's star has been slowly dimming over the past century. It's faded by about 14% in a 100 years. This long-term dimming is completely separate from the short-term dips, and suggests multiple phenomena might be affecting the star simultaneously. Recent observations have provided some clues. When the star dims, different colours of light are blocked by different amounts. Blue light is blocked more than red light, which suggests that whatever is causing the dimming is made of particles smaller than a micrometer. This pattern is consistent with dust, but not the kind of dust that should exist around a mature star like this one. One emerging theory involves circumstellar material, clouds of gas and dust orbiting the star at various distances. But Tabby's star is too old to have the protoplanetary disk of a young star, and too young to have the dust shells of a dying star. The material would need to be continuously replenished by some unknown mechanism. HD 1897 Thrusthiroid looks like a beautiful blue marble from space, almost Earth-like in its azure colouring. But this giant exoplanet, located 63 light-years away, is one of the most hellish worlds ever discovered. Its blue colour doesn't come from oceans. It comes from a high-temperature atmosphere where silicate particles form glass that rains sideways in winds reaching 7,000 kilometres per hour. fast enough to circle Earth in less than 6 hours. This planet is a hot Jupiter, a gas giant orbiting extremely close to its star, just 4.5 million kilometres away, 13 times closer than Mercury is to our Sun. At this distance, HD 89733b completes an orbit in only 2.2 Earth days. The proximity creates temperatures that soar to 2100 E on the day side, hot enough to melt silver, but that's just the beginning of this world's extreme conditions. The blue colour that makes it look deceptively Earth-like comes from silicate particles in its atmosphere. At these extreme temperatures, silicates, the same minerals that make up most of Earth's rocks, vaporise and then condense into tiny glass particles in the atmosphere. These particles preferentially scatter blue light, giving the planet its distinctive colour. But unlike Earth's peaceful blue, this is the blue of superheated glass. What happens next defies imagination. The temperature difference between the planet's day side and night side, about 500 degrees, drives the most extreme winds in the known universe. These hypersonic winds whip around the planet at 7,000 km/h, carrying the glass particles horizontally through the atmosphere. As these particles move from the hot day side to the cooler night side, they condense into larger droplets and rain down, but the ferocious winds blow this glass rain sideways rather than letting it fall vertically. Observations from the Hubble and Spitzer space telescopes revealed these conditions by studying how the planet's atmosphere absorbs and emits light. When HD 89733b passes behind its star, astronomers can measure the heat coming from different parts of the planet. They discovered that the hottest spot isn't directly under the star but shifted eastward by the incredible winds. This offset showed just how powerful the atmospheric circulation must be. The planet is tidally locked, meaning the same side always faces its star, like the Moon with Earth. This creates a permanent day side and night side. On the day side, temperatures are hot enough to vaporise iron. The night side, while cooler, still reaches temperatures around 700 Dunkelung. Between these extremes, at the terminator line where day meets night, conditions are especially violent as hot and cold air masses clash. The atmosphere itself is composed mainly of hydrogen and helium, like Jupiter, but with exotic additions. Besides the silicate particles, spectrographic analysis has detected water vapour, carbon monoxide, and possibly methane. These molecules are being constantly created and destroyed by the intense radiation from the nearby star. The upper atmosphere is actually evaporating into space, creating a comet-like tail of gas streaming away from the planet. HD 89733b's host star adds another layer of danger. It's highly active, frequently erupting with flares that blast the planet with X-rays and ultraviolet radiation. During these flares, the planet's evaporation rate increases dramatically. Astronomers have watched the planet's atmosphere puff up and stream away during particularly intense stellar storms. Over millions of years, this process could strip away a significant portion of the planet's gas envelope. The glass rain itself would be invisible to human eyes. The particles are too small, and the atmosphere too thick and turbulent. But if you could somehow survive the temperature and pressure, you would experience something like being inside a sideways sandblaster filled with microscopic glass shards moving at 7 times the speed of sound. In the southern sky, in the direction of the constellation Eridanus, there's a region of space that's measurably colder than everything around it. This CMB cold spot spans an enormous 1.8 billion light-years across and shows up as a distinctive blue patch in maps of the cosmic microwave background radiation. According to our best theories of how the universe evolved, a cold spot this large shouldn't exist. Yet there it is, challenging our fundamental understanding of cosmology. The cosmic microwave background, CMB, is the oldest light in the universe, released when atoms first formed 380,000 years after the Big Bang. This radiation fills all of space and is remarkably uniform, varying by only tiny amounts, typically just 18 millionths of a degree. But the cold spot is different. it's about 70 millionths of a degree colder than its surroundings, making it stand out like a cosmic bruise against the otherwise smooth background radiation. When astronomers first detected the cold spot in 2004 using data from NASA's WMAP satellite, many assumed it was a measurement error, but subsequent observations by the European Space Agency's Planck satellite confirmed its existence with even greater precision. The anomaly is real, and it's been there since the universe was young. Light from the CMB has been travelling for 13.8 billion years, so we're seeing this cold region as it existed when the universe was only 380,000 years old. The standard model of cosmology predicts that we should see random hot and cold spots in the CMB, caused by tiny quantum fluctuations in the early universe that were stretched to cosmic scales by inflation. But these fluctuations should follow a specific statistical distribution. The cold spot is too large and too cold to fit this distribution. The probability of such an extreme cold spot appearing by chance is less than 2%, making it a significant anomaly. Investigation revealed that the cold spot corresponds to an enormous cosmic void, a region of space containing far fewer galaxies than average. This supervoid, as astronomers call it, stretches about 1.8 billion light-years across and is located about 3 billion light-years from Earth. It's not completely empty, but contains about 10,000 fewer galaxies than a typical region of the same size. This represents a density about 30% lower than the cosmic average. The connection between the void and the cold spot involves something called the integrated Sachs-Wolf effect. When light from the CMB enters a large void, it gains energy falling into the gravitational well. As it climbs out the other side, it should lose that same energy. But in our expanding universe, the void grows larger while the light is crossing it. By the time the light exits, the gravitational well is shallower, so the light doesn't lose as much energy climbing out as it gained falling in. This leaves the light slightly cooler, but calculations show this effect can only account for about 10% of the observed temperature drop. Some physicists have proposed that the cold spot might be evidence of parallel universes. In this scenario, a universe collided with another universe in a higher dimensional space during cosmic inflation. The collision would leave an imprint in the CMB, essentially a bruise from the impact. While this sounds like science fiction, the mathematics of eternal inflation does predict that such collisions are possible, though most cosmologists remain skeptical. Another possibility is that the cold spot represents a texture, a type of cosmic defect left over from phase transitions in the early universe. Just as water can freeze with imperfections in its crystal structure, the universe might have cooled with topological defects in space-time itself. A texture would appear as a cold spot in the CMB, though most models suggest textures should be much smaller than what we observe. 55 Cancri is a planet that would make the world's diamond cartels nervous. This super-Earth, located 41 light-years away in the constellation Cancer, appears to be made largely of crystallized carbon, essentially a planet-sized diamond. With a mass 8 times that of Earth packed into a body just twice Earth's diameter, this carbon planet represents a completely different type of world than anything in our solar system. The planet orbits its sun-like star in just 18 hours, staying so close that surface temperatures reach 2400 Kelvin on the day side. At these temperatures and the extreme pressures inside the planet, carbon doesn't exist as the graphite we know from pencils. It forms diamond and other exotic carbon compounds. Scientists estimate that at least a third of the planet's mass is pure carbon, compared to less than 0.1% for Earth. The discovery challenged our Earth-centric assumptions about planetary composition. In our solar system, rocky planets like Earth are made mostly of oxygen, silicon, magnesium and iron. We assumed other rocky planets would have similar compositions, but 55 Cancri appears to have formed in a disk that was rich in carbon and poor in oxygen, creating a fundamentally different type of chemistry. Instead of the silicate rocks that dominate Earth, this planet likely has rocks made of silicon carbide and titanium carbide. Yale researchers who modelled the planet's interior in 2012 suggested it might have a diamond layer hundreds of kilometres thick beneath its surface. The pressure at these depths would be millions of times Earth's atmospheric pressure, perfect conditions for forming diamond from carbon. Above this diamond layer might be a relatively thin crust of graphite and other carbon compounds. The core could be made of iron, carbon and silicon carbide. But 55 Cancri's extreme nature doesn't stop with its composition. The planet is tidally locked, meaning one side permanently faces its star while the other faces eternal darkness. The day side is hot enough to melt iron, while the night side drops to a comparatively cool wall 100 degrees. This temperature difference drives supersonic winds that try to equalize the heat, creating a perpetual storm system that wraps around the planet. Recent observations by NASA's Spitzer Space Telescope detected huge variations in the planet's heat emission. Sometimes the hotspot is directly under the star, sometimes it's shifted eastward, and sometimes it seems to disappear entirely. One theory suggests the planet might have massive volcanic activity that periodically resurfaces large areas with lava. On a carbon planet, this wouldn't be silicate lava like on Earth. It might be exotic carbide lavas with properties we can barely imagine. The atmosphere, if it exists, would be unlike anything in our solar system. Models suggest it might contain carbon monoxide and carbon dioxide, but at these temperatures, even these gases behave strangely. Some scientists propose the atmosphere might have clouds of condensed carbon, essentially soot particles that rain down and compress into diamond at the surface. Others suggest the day side might be too hot to retain any atmosphere at all. What makes 55 Cancri especially intriguing is that it might not be unique. If planets can form from carbon-rich material, there might be many carbon planets throughout the galaxy. These worlds would have completely different geology, chemistry, and potential for life than the oxygen-rich worlds we're familiar with. On a carbon planet, the basic chemistry of life, if it could exist, would have to be fundamentally different. The planet's host star, 55 Cancri, is particularly rich in carbon compared to our Sun. This supports the theory that the planet formed from carbon-rich material. The system also contains at least 4 other planets, making it one of the most planet-rich systems known. The other planets appear to be more conventional gas giants, suggesting that 55 Cancri formed under special conditions. Magnetars are the universe's most powerful magnets, neutron stars with magnetic fields so intense they defy human comprehension. A typical magnetar has a magnetic field of about 10-15 Gauss. That's a quadrillion times stronger than Earth's magnetic field and 1,000 times stronger than a typical neutron star. From 1,000 kilometers away, a magnetar's field would not just wipe your credit cards, it would rip apart your molecular structure by distorting the electron clouds in your atoms. These cosmic monsters form when massive stars, at least 30 to 40 times the mass of our Sun, explode as supernovas and their cores collapse. During this collapse, the star's magnetic field gets compressed and amplified to unimaginable strengths. The result is a city-sized object about 20 kilometers across, with a magnetic field strong enough to kill you from the distance of the Moon. At 1,000 kilometers, the magnetic forces would be lethal to any known form of matter. The magnetic field of a magnetar is so strong, it fundamentally alters the properties of space around it. In the quantum vacuum near a magnetar's surface, the magnetic field can split photons and create particle-antiparticle pairs from pure energy. The field literally tears apart the fabric of empty space. Atoms themselves become distorted, stretched into long, needle-like shapes 200 times narrower than normal. Chemistry as we know it cannot exist in such conditions. SGR 180620 is one of the most powerful magnetars known. On December 27, 2004, it experienced a starquake, a readjustment of its crust caused by magnetic stress. In just 0.2 of a second, it released more energy than our Sun emits in 250,000 years. The burst of gamma rays was so intense that it bounced off the moon and lit up Earth's atmosphere from 50,000 light-years away. It actually compressed our planet's magnetic field and partially ionized the upper atmosphere. The surface of a magnetar is unlike anything else in the universe. The crust is made of iron nuclei arranged in a crystalline lattice, but compressed to densities billions of times greater than any material on Earth. This crust experiences enormous stress from the magnetic field, which can crack it like an eggshell. When the crust fractures, it releases bursts of X-rays and gamma rays that can be detected across the galaxy. These starquakes also create seismic waves that ring through the star like a bell. Life on a magnetar would be impossible in ways that challenge imagination. At the surface, the magnetic field would be about 1014 Gauss. In such a field, atoms are compressed into thin cylinders and can only move along magnetic field lines. The field is so strong it affects photons themselves. X-rays become polarized and can split in two, while radio waves can merge together. The very nature of light changes in these conditions. The magnetic field also makes the space around a magnetar intensely energetic. Charged particles get accelerated to nearly the speed of light, creating a magnetosphere crackling with electricity. The voltage differences can reach 1016 volts, enough to accelerate particles to energies far beyond what our most powerful particle accelerators can achieve. This creates a constant fireworks display of high-energy radiation that would sterilize any normal matter within millions of kilometers. Magnetars don't last forever in their extreme state. Their magnetic fields decay over time, taking about 10,000 years to weaken significantly. As the field weakens, the starquakes become less frequent and less powerful. Eventually, after about 1 million years, they fade into ordinary neutron stars. This short lifetime means magnetars are rare. Only about 30 are known in our galaxy compared to over 2,000 regular pulsars. The origin of these extreme magnetic fields is still debated. One theory suggests they form through a dynamo effect during the first few seconds of the neutron star's life, when it's rotating extremely rapidly and still has differential rotation between its core and crust. Another possibility is that some massive stars are born with unusually strong magnetic fields that get amplified during collapse. WASP-76b makes hell look temperate. On this ultra-hot Jupiter, located 640 light-years away in the constellation Pisces, temperatures soar so high that iron vaporizes on the day side, gets carried by ferocious winds to the night side, and then rains down as molten metal droplets. It's a world where the weather forecast includes showers of liquid iron falling from clouds of metal vapor. This planet orbits its star at a distance of just 4.8 million kilometers, 12 times closer than Mercury is to our Sun. At this proximity, WASP-76b is tidally locked, with one face permanently cooking under its star's glare, while the other side faces eternal darkness. The temperature difference is extreme. The day side reaches 2400 °C, hot enough to vaporize iron, while the night side cools to about 1500 Gandenzo, where iron condenses back into liquid. The discovery of iron rain came from studying the planet's atmosphere using the espresso instrument on the Very Large Telescope in Chile. When astronomers analysed light passing through the atmosphere at the day-night boundary, they detected strong iron vapour signatures on the evening edge, but not on the morning edge. This asymmetry revealed what was happening. Iron vaporizes on the scorching day side, gets swept to the night side by winds exceeding 18,000 km/h, and precipitates out as it cools. But iron isn't the only metal in WASP-76b's bizarre weather system. The extreme temperatures vaporize a whole suite of elements that would be solid rocks on Earth. Magnesium, calcium, chromium, and even titanium exist as gases in the dayside atmosphere. As these metal vapors get carried to the cooler night side, they condense at different temperatures, creating a complex precipitation pattern. Iron rain might be accompanied by showers of liquid titanium or magnesium, each falling in different regions based on the local temperature. The planet's atmosphere itself is puffed up by the intense heat, extending far beyond what would be normal for a planet of its mass. This extended atmosphere is constantly being stripped away by stellar radiation, creating a comet-like tail of gas streaming behind the planet. WASP-76b is literally evaporating, losing millions of tons of atmosphere every second. Despite this, its huge mass means it would take billions of years to lose a significant fraction of its material. Spectroscopic observations have revealed even more bizarre chemistry. The day side is so hot that molecules break apart into individual atoms. Water vapour dissociates into hydrogen and oxygen. Methane can't exist, and even typically stable molecules like titanium oxide are destroyed. This atomic gas glows with its own light, making the day side of the planet luminous like a stellar atmosphere rather than a normal planetary one. The winds on WASP-76b are driven by the enormous temperature gradient between day and night. Hot gas on the day side expands and flows toward the night side, where it cools and sinks. This creates a circulation pattern that wraps around the entire planet. But unlike Earth's trade winds, these carry vaporized rock and metal. The wind speeds are supersonic, creating shock waves where different air masses collide at the terminator line. Recent models suggest the iron rain might not fall vertically like rain on Earth. The extreme winds could blow the droplets almost horizontally, creating a kind of metallic sleet that scours the night side of the planet. The droplets themselves would glow red hot as they fall, creating a hellish light show in the eternal darkness. Some models suggest the iron might even form clouds before precipitating, creating layers of metal vapour at different altitudes based on temperature. The surface of WASP-76b, if it has one, would be impossible to observe directly. The atmosphere is opaque to most wavelengths of light, and the extreme conditions make it unclear whether there's a solid surface at all, or just increasingly dense layers of gas. If a surface exists, it might be covered in lakes or oceans of molten metal, fed by the constant iron rain. These metal seas would have properties unlike any liquid on Earth, highly reflective, incredibly dense, and hot enough to glow. The planet's host star adds another layer of complexity. It's slightly hotter and larger than our Sun, blasting WASP-76b with intense ultraviolet and X-ray radiation. This stellar radiation doesn't just heat the planet, it ionizes the upper atmosphere, creating a plasma layer where atoms are stripped of their electrons. This ionized layer interacts with any magnetic field the planet might have, potentially creating aurora displays made of glowing metal ions. What makes WASP-76b particularly valuable to astronomers is that it's an extreme natural laboratory. The same processes that create iron rain operate on other hot Jupiters, just at less extreme levels. By studying this planet, scientists can better understand atmospheric dynamics, chemistry under extreme conditions, and how planets evolve when subjected to intense stellar radiation. It's helped confirm theories about atmospheric circulation on tidally locked worlds that were previously just mathematical models. The discovery also raises questions about planet formation. How did WASP-76b end up so close to its star? Most theories suggest it formed farther out and migrated inward, but the mechanism is debated. Its current orbit is actually slowly decaying due to tidal forces. The planet will eventually spiral into its star, though this will take millions of years. Until then, it continues its bizarre existence as a world where metal falls from the sky. The universe has architecture on a scale that defies human comprehension. In 1989, astronomers discovered the CFA2 Great Wall, a colossal structure of galaxies stretching over 500 million light-years long, 300 million light-years wide, and 15 million light-years thick. Since then, even larger structures have been found, including the Sloan Great Wall at 1.38 billion light-years long. These cosmic walls are the largest known structures in the universe, and they shouldn't exist according to standard cosmological principles. These walls aren't solid structures, but vast collections of galaxies arranged in sheet-like formations. They're part of the cosmic web, the largest scale structure of the universe, where galaxies cluster along filaments and walls surrounding enormous voids. The Sloan Great Wall alone contains hundreds of thousands of galaxies, each with hundreds of billions of stars. The amount of matter in these structures is measured in millions of galaxy masses. The problem is that these walls are too big for the age of the universe. According to the cosmological principle, the universe should be roughly homogeneous on large scales. Zoom out far enough and everything should look more or less the same. But these walls represent density variations that challenge this assumption. Computer simulations of structure formation struggle to produce walls this large in the time available since the Big Bang. The discovery came from massive galaxy surveys that mapped millions of galaxies in 3 dimensions. The Sloan Digital Sky Survey, which found the Sloan Great Wall, used a dedicated telescope to systematically photograph large portions of the sky. By measuring the redshift of galaxies, how much their light is stretched by the expansion of space, astronomers could determine their distances and create 3D maps of the universe's structure. What emerged from these surveys was breathtaking. The universe isn't randomly scattered with galaxies. Instead, it resembles a cosmic spiderweb or neural network, with dense walls and filaments of galaxies separated by vast, nearly empty voids. The walls form where multiple filaments intersect, creating 2-dimensional sheets of galaxies. These structures are held together by gravity, with dark matter providing most of the gravitational scaffolding. The formation of these walls traces back to the earliest moments after the Big Bang. Tiny quantum fluctuations in the density of matter were amplified by cosmic inflation and gravity over billions of years. Regions that were slightly denser attracted more matter, while less dense regions became voids. This process, called gravitational instability, created the cosmic web we see today. But the sheer size of the Great Wall suggests this process worked faster or more efficiently than our models predict. Recent discoveries have pushed the boundaries even further. The Boss Great Wall, discovered in 2016, spans over 1 billion light-years. The Hercules Corona Borealis Great Wall, identified through gamma-ray burst positions, might stretch 10 billion light-years, though its existence as a single structure is debated. If real, it would encompass about 11% of the observable universe's diameter. Dark matter plays a crucial role in these structures. Observations show that visible galaxies trace only about 10% of the total mass in the walls. The rest is dark matter, forming an invisible skeleton that guides where galaxies form. Without dark matter's extra gravity, these walls couldn't have formed in the time available. The galaxies we see are just lights decorating a much larger invisible framework. The walls aren't static. They're growing as gravity pulls in more galaxies from surrounding regions. Where walls intersect, galaxy clusters form, the densest concentrations of matter in the universe. These clusters can contain thousands of galaxies bound together by gravity. The walls act as highways, channeling galaxies toward these intersection points. This flow of galaxies along the walls has been measured and confirms our understanding of cosmic structure formation. Studying these walls helps cosmologists understand the universe's larger scale properties. They serve as laboratories for testing theories about dark matter, dark energy, and the universe's expansion. The distribution of walls and voids also preserves information about the early universe, acting as a fossil record of conditions shortly after the Big Bang. US 708 is a stellar speed demon, racing through space at 2,100 kilometers per second, fast enough to travel from Earth to the Moon in just 5 minutes. This hypervelocity star isn't just breaking cosmic speed limits. It's been violently ejected from our galaxy and is now on an unstoppable journey into intergalactic space. What makes this even more extraordinary is that US 708 is the fastest star ever discovered that wasn't accelerated by our galaxy's central black hole. This stellar outcast is a hot subdwarf star, a type of evolved star that has lost most of its outer hydrogen envelope. Located about 62,000 light-years from Earth, US 708 is moving at speeds that exceed our galaxy's escape velocity by a factor of 2. While most stars orbit the galactic centre at a leisurely 200-250 km/s, this star is travelling at nearly 5 times that speed. At this velocity, no force in the galaxy can hold it back. The story of how US 708 achieved such incredible speed involves one of the universe's most violent events. Astronomers believe this star was once part of a binary system with a white dwarf companion. The two stars orbited each other in an increasingly tight spiral as the white dwarf stripped material from US 708. Eventually, the white dwarf accumulated enough mass to trigger a Type Ia supernova, a thermonuclear explosion that completely destroyed it. But here's where it gets strange. In a normal supernova, both stars would be destroyed or the companion would receive a modest kick. US 708 experienced something far more extreme. Evidence suggests it was orbiting so close to the white dwarf, possibly within its outer layers, when the explosion occurred. The supernova didn't just give us 708 a push, it acted like a cosmic slingshot, converting all of the binary system's orbital energy into pure velocity. The star bears the scars of this violent past. Its surface is enriched with heavy elements that could only have come from being inside a supernova explosion. The extreme conditions stripped away most of its hydrogen, leaving behind a compact helium-rich core. US 708 is also rotating incredibly fast, about once every 10 minutes, likely spun up by mass transfer from its deceased companion. What makes US 708 unique among hypervelocity stars is its trajectory. Most fast-moving stars were ejected from near the galactic centre by interactions with the supermassive black hole there. But US 708's path traces back to the galactic disk, proving it was ejected by a supernova. This makes it the first confirmed example of a star being shot out of the galaxy by a stellar explosion rather than a black hole encounter. The physics of the ejection are extreme. For US 708 to reach 1/200 km/s, it must have been orbiting the white dwarf at an even higher velocity when the explosion occurred. Models suggest the two stars were separated by less than the radius of our Sun, completing an orbit in just 10 minutes. When the white dwarf detonated, US 708 was instantly released from this frantic orbital dance, maintaining its incredible speed as it shot away. US 708's journey will never end. At 200 km/s, it will escape not just our galaxy, but our entire local group of galaxies. In about 25 million years, it will leave the Milky Way entirely and enter the lonely expanse of intergalactic space. From there, it will wander the universe alone, a stellar exile carrying the chemical evidence of its violent origin. The discovery has important implications for understanding both supernovas and galaxy evolution. If stars can be ejected at such speeds by supernovas, then galaxies are slowly losing stars to intergalactic space. Over cosmic time, countless stars may have been flung out of their home galaxies, populating the vast spaces between them. US 708 also helps astronomers understand the extreme binary systems that create Type A supernovas. Finding US 708 required combining data from multiple surveys and looking for stars with unusual properties. Its extreme velocity was confirmed using precise spectroscopic measurements that showed how fast it's moving away from us. The star's chemical composition, determined from its spectrum, provided the crucial clues about its supernova origin. Tris 2b is the darkest planet ever discovered, a world so black it makes coal look reflective. This Jupiter-sized exoplanet, located 750 light-years away, absorbs 99% of all light that strikes it, reflecting less than 1% back into space. It's darker than black acrylic paint, darker than charcoal, darker than any planet has a right to be. In the inky blackness of space, Tris 2b is nearly invisible, a shadow world that challenges our understanding of planetary atmospheres. The planet orbits extremely close to its star, just 5 million kilometers away. completing an orbit every 2.5 days. At this distance, temperatures on the day side reach 1/800 Celsius. You'd expect such a hot planet to glow with its own heat, and it does emit a faint deep red glow like a burning ember. But in terms of reflecting its star's light, Tris 2b is darker than the empty space around it. What makes this darkness so puzzling is that hot Jupiters typically have reflective clouds. Jupiter in our solar system reflects about 52% of sunlight due to its ammonia clouds. Even hot Jupiters usually have clouds of minerals like titanium oxide or vanadium oxide that reflect some light. But TAR-ES 2b seems to lack these reflective clouds entirely. Instead, its atmosphere appears to be filled with light-absorbing chemicals that trap photons like a cosmic roach motel. The leading theory involves exotic chemistry in the planet's superheated atmosphere. At 1300 Rudiascandil, most molecules break apart. Scientists think the atmosphere might contain vaporized sodium and potassium, which absorb light strongly in the visible spectrum. There might also be titanium oxide present, but in a form that absorbs light rather than reflecting it. Some models suggest the presence of gaseous aluminum oxide and titanium hydride, both powerful light absorbers, but chemistry alone can't explain the extreme darkness. The planet's albedo, reflectivity, of less than 1% is lower than any model predicts. Something else must be happening. One possibility is that TAR-ES 2b has a unique atmospheric structure, with no high-altitude haze or clouds to scatter light. The atmosphere might be incredibly clear, allowing light to penetrate deep where it's absorbed by hot gases and never escapes. Another factor could be the planet's magnetic field. If Tris 2b has a strong magnetic field, it might strip away reflective particles from the upper atmosphere, leaving only the light-absorbing gases, or the intense stellar radiation might be constantly destroying any reflective compounds that try to form, maintaining the planet's extreme darkness through a continuous chemical process we don't yet understand. The discovery of TAR-ES 2b's darkness came from incredibly precise measurements by the Kepler Space Telescope. By monitoring how the total light from the star system changed as the planet orbited, astronomers could determine how much light the planet reflected. The measurements had to be accurate to parts per million to detect such a dark world. Even then, astronomers initially thought their instruments were malfunctioning. TAR-ES 2b's darkness makes it a challenge to study. Most exoplanet observations rely on detecting reflected light or thermal emissions. With Tris 2b reflecting almost nothing and emitting only faint infrared radiation, it's like trying to study a black cat in a coal mine. Special techniques using phase curves, how the system's brightness changes as the planet orbits, have revealed some details about atmospheric circulation and temperature distribution. The extreme darkness has practical implications for understanding exoplanets. It shows that hot Jupiters can have much more diverse properties than expected. If planets can be this dark, it means some exoplanets might be hiding in our data, too dark to detect with current methods. It also raises questions about energy balance. A planet that absorbs 99% of incoming light must have efficient ways to redistribute or radiate that energy. Recent observations have detected subtle variations in Tris 2b's darkness. The planet seems to be slightly less dark at certain wavelengths, particularly in the infrared. This suggests the atmosphere isn't uniformly absorbing, but has a complex structure that varies with altitude and temperature. These variations might hold the key to understanding what makes this world so extraordinarily dark. In the constellation Bootes lies one of the most unsettling features of the cosmos, an enormous void containing almost no galaxies. The Bootes void, also called the Great Nothing, spans approximately 330 million light-years in diameter. While an average region of space this size should contain about 2,000 galaxies, the Bootes void contains only about 60. It's as if someone took a cosmic eraser and removed 97% of the galaxies that should be there. The void's discovery in 1981 shocked astronomers. As they mapped galaxy positions in this region, They expected to find the usual cosmic web structure, clusters and filaments of galaxies separated by smaller voids. Instead, they found a vast spherical region that was nearly empty. The few galaxies that do exist within the void are arranged in a tube-like structure running through the centre, leaving the rest of the space eerily vacant. What makes the Botha's void particularly mysterious is its sheer size. According to computer simulations of cosmic evolution, voids this large shouldn't have had time to form through normal processes. In the Standard Model, matter was distributed fairly evenly after the Big Bang. Gravity gradually pulled matter together, creating the cosmic web of galaxy clusters and voids we see today. But this process is slow. Creating a void 330 million light-years across should take longer than the current age of the universe. The void is often described as spherical, but recent surveys show it's more complex. It appears to be composed of smaller voids that merge together, like soap bubbles combining into one larger bubble. This structure suggests the void formed through a rare alignment of cosmic expansion patterns. Multiple smaller voids happened to form near each other and gradually merged as the universe expanded, creating one supervoid. At the centre of the void runs a sparse filament of galaxies, sometimes called a tube. This structure is about 50 million light-years wide and contains most of the void's galaxies. It's as if the galaxies that should fill the void were compressed into this single strand. Some astronomers think this tube might be the remnant of a cosmic web filament that survived whatever process cleared out the rest of the void. The existence of the Botha's void has profound implications for cosmology. It suggests that the universe's large-scale structure might be more varied than we thought. If one such massive void exists, there might be others we haven't discovered yet. Some cosmologists have proposed that supervoids like Botha's could be fossil remnants of the universe's inflationary epoch, regions where quantum fluctuations created unusually low density that persisted as the universe evolved. Dark energy might play a role in the void's expansion. In regions with fewer galaxies, dark energy's repulsive effect faces less opposition from gravity. This could cause voids to expand faster than denser regions, potentially explaining how the Botha's void grew so large. Some models suggest supervoids might be expanding up to 20% faster than the universe's average expansion rate. The void affects its surroundings in measurable ways. Galaxies near its edges are being pulled outward by the gravity of surrounding denser regions, causing the void to grow over time. Light passing through the void experiences gravitational effects that astronomers can detect. When cosmic microwave background radiation crosses the void, it emerges slightly cooler due to the integrated Sachs-Wolf effect. Studying the few galaxies within the void provides unique insights. These isolated galaxies evolved differently from those in dense clusters. They've had fewer interactions and mergers, potentially preserving more primordial characteristics. Some show unusual properties, like lower rates of star formation, possibly due to the lack of gravitational interactions that trigger stellar birth in denser regions. The Botha's void raises uncomfortable questions about our cosmic neighbourhood. If such massive voids can exist, how typical is our own region of space? Earth sits in a relatively dense part of the cosmic web. Had we evolved inside a supervoid, our view of the universe would be dramatically different. We might see far fewer galaxies and have a much harder time understanding cosmic structure. Recent surveys have found that the Botha's void might not be as empty as originally thought. Improved telescopes have detected faint dwarf galaxies previously too dim to see. But even accounting for these, the void remains severely underpopulated. It stands as one of the most extreme examples of cosmic emptiness, a vast region where the universe forgot to put galaxies. PSR J548 2446 AED is the universe's most extreme lighthouse, a dead star spinning 716 times every second. This pulsar rotates so fast that a point on its equator moves at 24% the speed of light. It completes more rotations in 1 second than a commercial jet engine does in a minute. The surface is moving so fast that if you could somehow stand on it, you'd be flung into space at 70,000 kilometers per second. This cosmic speed demon is a neutron star, the collapsed core of a massive star that exploded as a supernova. When the star died, its core compressed from something larger than our Sun down to a sphere just 20 kilometers across. This collapse preserved the star's angular momentum, causing it to spin faster, like an ice skater pulling in their arms. But PSR J1748 246 AD spins so fast it pushes the theoretical limits of what's possible. The neutron star is so dense that a teaspoon of its material would weigh about 1 billion tons on Earth. This incredible density allows it to hold together despite the extreme rotation. At 716 rotations per second, the centrifugal force at the equator is fighting a gravitational field 200 billion times stronger than Earth's. Any faster, and the star would tear itself apart. Scientists calculate that the absolute speed limit for neutron star rotation is around 1,000 to 1,500 rotations per second. PSR JL748 246 AD was discovered in 2004 in the globular cluster Terzan 5, about 18,000 light-years from Earth. Finding it required incredibly precise timing measurements. The pulsar emits beams of radio waves from its magnetic poles. As it spins, these beams sweep across space like a lighthouse. When a beam points at Earth, we detect a pulse. By timing these pulses to nanosecond precision, astronomers determine the rotation rate. But here's what makes this pulsar even stranger. It's not slowing down like it should be. Normal pulsars gradually lose rotational energy and spin slower over time. PSR J1748 2446 AD is in a binary system with a companion star, and it's actually stealing material from its partner. This infalling matter carries angular momentum, spinning the pulsar up like water from a hose hitting a water wheel. It's called a millisecond pulsar, though at 1.4 milliseconds per rotation. That name seems almost quaint. The magnetic field of this pulsar, while weaker than younger pulsars, is still about 100 million times stronger than Earth's. This field accelerates particles to near light speed, creating the radio beams we detect. The combination of rapid rotation and magnetic field turns the pulsar into a cosmic particle accelerator more powerful than anything humans could build. The energy output is staggering. It radiates more energy in 1 second than our Sun does in 3 years. The surface conditions are beyond extreme. The gravity is so strong that the escape velocity is about 1/3 the speed of light. Mountains on the surface can be no taller than a few millimeters before gravity crushes them. The magnetic field would rip apart any normal matter at the atomic level, and the rotation creates relativistic effects. Time dilation means that time passes slightly slower at the equator than at the poles. The companion star orbiting PSR J+S748 2446 Yard is slowly being consumed. The pulsar's gravity strips gas from its partner, which spirals inward and crashes onto the neutron star's surface. This process has been going on for millions of years and will continue until the companion is completely devoured. It's cosmic cannibalism on an unimaginable scale, with the pulsar growing slightly more massive and spinning slightly faster with each meal. Studying millisecond pulsars like PSR J1748 246 AD helps scientists test the laws of physics under extreme conditions. The dense matter inside neutron stars exists in states impossible to create on Earth, possibly including quark matter or other exotic phases. The precise timing of pulsar signals also makes them excellent cosmic clocks, useful for detecting gravitational waves and testing general relativity. In the constellation Sagittarius, near the centre of our galaxy, floats a massive cloud of alcohol and organic molecules that would taste like raspberries and smell like rum if you could somehow sample it without dying instantly in the vacuum of space. Sagittarius B2 is a giant molecular cloud containing vast quantities of ethyl formate, the chemical compound that gives raspberries their flavour and contributes to the smell of rum. This cosmic cocktail spans 150 light-years across and contains enough alcohol to supply every person on Earth with 300,000 pints of beer every day for 1 billion years. The cloud is a stellar nursery where new stars are being born, and the complex chemistry within it is creating a bewildering array of organic molecules. Among the 50 different molecules detected so far, ethyl formate stands out for its familiar terrestrial associations. The discovery came from analysing radio waves emitted by molecules in the cloud. Each type of molecule emits radio waves at specific frequencies when its atoms vibrate or rotate. By comparing these frequencies to laboratory measurements, astronomers can identify what molecules are present. In 2009, researchers using the IRAM telescope in Spain detected the distinctive signature of ethyl formate in Sagittarius B2. But don't imagine this as a pleasant-smelling cloud you could fly through. The density is still incredibly low by Earth standards, about 1 million molecules per cubic centimetre, compared to 1019 molecules per cubic centimetre in Earth's atmosphere. The cloud is also at temperatures around 170 degrees and contains deadly compounds like methanol, formaldehyde, and hydrogen cyanide. It's more like a frozen, poisonous wasteland that happens to contain trace amounts of raspberry flavouring. The presence of ethyl formate is significant because it's a relatively complex organic molecule containing carbon, hydrogen, and oxygen arranged in a specific pattern. Finding such molecules in space suggests that the building blocks of life might be more common than previously thought. Ethyl formate is a step toward amino acids, the components of proteins. If space clouds can cook up raspberry flavouring, they might also create more biologically important molecules. The cloud contains other fascinating molecules. There's ethanol, the alcohol in alcoholic beverages, in quantities that dwarf Earth's annual production. There's acetone, nail polish remover, ammonia, cleaning fluid, and methanol, wood alcohol. It's like a cosmic chemistry set creating random organic compounds. The variety suggests that space chemistry is far more complex and productive than scientists initially believed. These molecules form through a variety of processes. Some are created on the surface of dust grains where atoms can stick and react. Others form through gas phase reactions when molecules collide in space. Ultraviolet radiation from nearby stars provides energy to drive chemical reactions. The process is slow by Earth standards, taking millions of years, but the cloud is so vast that enormous quantities accumulate. Sagittarius B2 is particularly rich in organic molecules because of its location near the galactic centre. The increased stellar density means more supernovas, which create heavy elements and dust grains. The stronger radiation field drives more complex chemistry. The cloud is also massive enough that its interior is shielded from destructive radiation, allowing delicate molecules to survive. The discovery has implications for understanding how life might have started on Earth. Some scientists propose that organic molecules from space, delivered by comets and meteorites, might have seeded early Earth with the precursors to life. If clouds like Sagittarius B2 are common throughout the galaxy, then the basic ingredients for life might be everywhere, just waiting for the right conditions to evolve into something more complex. Finding ethyl formate required incredibly sensitive instruments and patient observation. The molecule's radio signature is weak and easily lost among stronger signals from simpler molecules. Astronomers had to observe for many hours and use sophisticated computer analysis to tease out the telltale frequencies. It's like hearing a whisper in a noisy room, possible but requiring careful attention and the right tools. In 2012, astronomers witnessed something that should have been impossible, a star that survived being eaten by a black hole. The star, dubbed S5HVS1, came so close to the supermassive black hole at the centre of our galaxy that it should have been torn apart by tidal forces. Instead, it was flung out of the galaxy at 700 kilometers per second, making it one of the fastest moving stars ever discovered. It's the stellar equivalent of escaping from a shark's mouth. This cosmic Houdini act occurred at Sagittarius A, the 4 million solar mass black hole lurking in the Milky Way's core. When S5HVS1 ventured too close, Everyone expected a typical tidal disruption event. The star should have been stretched into spaghetti and devoured. But something extraordinary happened. The star was part of a binary system, and the complex three-body interaction between the two stars and the black hole created a gravitational slingshot that saved one star while sacrificing the other. The physics of this escape are mind-bending. As the binary star system approached the black hole, the gravitational field began affecting each star differently. The star closer to the black hole experienced stronger gravity than its partner. This differential force started pulling the binary system apart. At the critical moment, one star was captured by the black hole, while the other was ejected at enormous speed, carrying away the binary system's orbital energy as kinetic energy. S5 HVS1 is now travelling so fast it will escape the Milky Way entirely. In cosmic terms, it's been given a one-way ticket out of the galaxy. The star will spend the rest of its life journeying through intergalactic space, a lonely exile bearing witness to its narrow escape. Chemical analysis of the star shows it's relatively normal, a main sequence star about 2.35 times the mass of our Sun, but its velocity makes it one of the most extreme objects in the galaxy. The discovery came from the Southern Stellar Stream Spectroscopic Survey, which was actually looking for something else entirely. Astronomers were mapping stellar streams, remnants of dwarf galaxies torn apart by the Milky Way, when they noticed a star moving at impossible speeds. Follow-up observations traced its trajectory back to the galactic centre, revealing its dramatic origin story. The precision required to make these measurements is extraordinary, like tracking a bullet fired from 25,000 light-years away. This isn't the only star to survive a close encounter with a black hole, but it's one of the most extreme cases documented. Other hypervelocity stars have been discovered, but most were rejected by interactions with stellar mass black holes or binary star dynamics. S5 HVS1's encounter with a supermassive black hole and its survival make it unique. It's proof that even in the most extreme gravitational environments, complex dynamics can create surprising outcomes. The event also tells us about conditions near the galactic centre. The region around Sagittarius A is packed with stars moving at high speeds in chaotic orbits. Binary systems that wander too close get torn apart in what astronomers call the Hills mechanism, named after astronomer Jack Hills, who first proposed this ejection method. S5 HVS1 proves this mechanism works even with supermassive black holes, not just stellar mass ones. For the companion star that didn't escape, the fate was less fortunate. It either plunged directly into the black hole or entered such a tight orbit that it was eventually torn apart and consumed. This stellar sacrifice is what gave S5 HVS1 the energy to escape. In a sense, one star died so the other could achieve the highest velocity escape ever recorded from a supermassive black hole encounter. The implications extend beyond just one star's story. If stars can be ejected at such speeds, then galaxies are slowly losing stars to intergalactic space. Over billions of years, countless stars may have been flung out by black hole encounters. These hypervelocity stars could be carrying planets with them, creating rogue planetary systems hurtling through the void. Some might even harbour life, making them the ultimate generation ships. Empty space isn't as empty as we thought. Quantum field theory predicts that the universe could contain bubbles of true vacuum, regions where space has dropped to an even lower energy state than the rest of the cosmos. These bubbles of nothing would expand at the speed of light, destroying everything in their path and rewriting the laws of physics as they go. It's cosmic destruction on the largest possible scale, and it might already be happening somewhere in the universe. The terrifying possibility comes from our understanding of the Higgs field, which gives particles their mass. Current measurements suggest the Higgs field might be in a metastable state, like a ball perched on a shelf rather than on the floor. It appears stable, but given the right nudge, it could fall to a lower energy state. If this happened anywhere in the universe, it would create a bubble of true vacuum that would expand outward at light speed, converting our false vacuum universe into something fundamentally different. Inside these bubbles, physics would be alien. The masses of fundamental particles would change. Atoms might not be stable. Chemistry as we know it couldn't exist. Any matter entering the bubble would be instantly destroyed and converted into whatever new forms of matter the new physics allows. It wouldn't be an explosion in the conventional sense. It would be reality itself being rewritten at the most fundamental level. Expansion would be unstoppable. Since the bubble wall moves at light speed, you'd have no warning. The night sky would look normal until the instant the bubble reached Earth. Then, in less time than it takes light to cross a proton, you and everything around you would cease to exist in any recognizable form. The bubble would continue expanding forever, eventually converting the entire observable universe to the new vacuum state. What could trigger such a catastrophe? High-energy particle collisions might do it, though calculations suggest the energies required are far beyond anything humans can create. Some physicists worried that the Large Hadron Collider might trigger vacuum decay, but the cosmic ray collisions happening naturally in Earth's atmosphere are far more energetic and haven't destroyed us yet. More likely triggers might be extreme conditions near black holes or in the early universe. The possibility isn't just theoretical. Some interpretations of cosmic inflation, the rapid expansion of the early universe, suggest it ended when a false vacuum state decayed to a lower energy state. If this happened once, it could happen again. The current vacuum might just be another meta-stable state waiting for the right conditions to decay further. We could be living in a temporary phase of the universe's existence. Recent precision measurements of the Higgs boson's mass and the top quark's mass put our universe suspiciously close to the boundary between stable and metastable vacuum. If the measurements are correct, we're balanced on a knife's edge. A slightly different value would mean either certain stability or certain doom. This cosmic coincidence troubles physicists and might hint at deeper principles we don't yet understand. Even more disturbing is that vacuum decay might have already started somewhere. If a bubble formed 1 billion light-years away, it would be expanding toward us right now, invisible and undetectable until it arrives. There could be multiple bubbles expanding through the universe, destined to meet and merge until everything is converted. The observable universe might be shrinking as these bubbles consume galaxies beyond our cosmic horizon. Some cosmologists find comfort in the anthropic principle. We must live in a stable or metastable vacuum because otherwise we wouldn't exist to observe it. But this offers cold comfort if our vacuum is merely metastable. It just means we've been lucky so far. The universe has existed for 13.8 billion years without vacuum decay, but that doesn't guarantee it will last another day. There might be ways to detect approaching vacuum decay bubbles, though they'd give little warning. The bubble wall would be preceded by high-energy particles and radiation. Gravitational effects might be detectable as the bubble approaches, but by the time these signals reached us we'd have only minutes or hours before the bubble itself arrived. It would be like seeing the flash of a nuclear explosion. By then, it's too late. HD 89-73b takes the concept of windy weather to apocalyptic extremes. On this hellish exoplanet, winds rage at 2 kilometers per second, that's 70,100 kilometers per hour, or about 7 times the speed of sound on Earth. These hypersonic gales are so fast they could circumnavigate Earth in just 5.5 hours. It's not just a breeze, it's a permanent planet-wide catastrophe that would instantaneously shred any known material. This hot Jupiter orbits its star every 2.2 days at a distance of just 4.5 million kilometers. Being tidally locked, one side faces eternal day, while the other endures eternal night. This creates a temperature differential of nearly 500 Canlana between the day and night sides, and nature abhors such imbalances. The atmosphere responds with the most violent winds ever measured, desperately trying to equalize temperatures between the superheated day side at 200 Orient and the merely hellish night side at 700 North. Scientists discovered these supersonic winds by studying the planet's atmosphere during transits. As HD 89NTF33b passes in front of its star, some starlight filters through the atmosphere. By analysing how this light changes at different wavelengths, astronomers can detect which chemicals are present and how fast they're moving. The Doppler shift of sodium and iron atoms revealed velocities that left researchers double-checking their calculations. The winds create a strange atmospheric pattern. Instead of flowing directly from hot to cold like Earth's winds, they form a supersonic jet stream that wraps around the planet's equator. This jet moves so fast it actually outruns the planet's rotation, creating a kind of atmospheric superrotation. The hottest spot on the planet isn't where the star shines most directly, but is shifted eastward by about 30 degrees due to these incredible winds. At 2 kilometers per second, these winds carry enormous kinetic energy. On Earth, hurricane winds of 250 km/h can destroy buildings. HD 1897333b's winds pack nearly 900 times more energy per unit mass. If such winds existed on Earth, they wouldn't just destroy cities, they'd scour the surface down to bedrock. The atmospheric pressure waves would create continuous sonic booms that would shatter any solid material. The mechanism driving these winds is fascinating. The intense stellar radiation on the day side causes atmospheric gases to expand dramatically. This creates a pressure gradient of unprecedented strength. Unlike Earth, where the Coriolis effect from rotation helps organise winds into cyclones, HD 1897333b's tidal locking creates a simpler but more extreme pattern. The atmosphere essentially tries to explode away from the day side, creating a shock wave that propagates around the planet. These winds carry more than just heat. They transport exotic materials around the planet. On the day side, temperatures are high enough to vaporize rocks and metals. These vapors get swept to the night side by the winds where they cool and condense. Iron and silicate clouds form and precipitation falls, not as rain, but as molten metal and liquid glass droplets moving horizontally at supersonic speeds. The winds significantly affect the planet's observable properties. They smooth out temperature variations that would otherwise be more extreme. They also create a complex three-dimensional circulation pattern, with gases rising on the day side, flowing to the night side at high altitude, sinking and returning at lower altitudes. This creates multiple jet streams at different heights, each racing around the planet at supersonic speeds. Recent computer models suggest the winds might be even more complex than initially thought. Interactions between the planet's possible magnetic field and its ionized atmosphere could create additional acceleration. The winds might also vary with the stellar cycle, becoming even more extreme during stellar flares. Some models predict localized wind speeds could exceed 3 km/s in certain regions. The discovery of such extreme winds has implications for understanding atmospheric dynamics throughout the universe. They show that atmospheres can remain stable, even under conditions that would seem impossibly violent. They also demonstrate that heat transport on tidally locked worlds operates under fundamentally different principles than on rotating planets like Earth. NGC 1052 DF2 shouldn't exist. This ghostly galaxy, located 65 million light-years away, appears to be missing nearly all of its dark matter. In a universe where dark matter outweighs visible matter by 5 to 1, finding a galaxy with almost none is like finding a car with no engine. It challenges our fundamental understanding of how galaxies form and survive. The galaxy has 400 times less dark matter than astronomers would expect for a galaxy of its size. The discovery in 2018 sent shockwaves through the astronomical community. Using the Dragonfly telephoto array, astronomers measured the velocities of 10 globular clusters orbiting the galaxy. These measurements revealed that NGC 1052 DF2 has almost exactly the mass you'd expect from its visible stars alone, about 200 million times the mass of our Sun. There's simply no room for significant amounts of dark matter. This absence is deeply puzzling, because dark matter is thought to be essential for galaxy formation. In the standard model, dark matter clumps together first, creating gravitational wells that attract normal matter. Galaxies form inside these dark matter halos like puddles forming in depressions. Without dark matter's gravitational scaffolding, galaxies shouldn't be able to form or hold together. Yet NGC 1052 DF2 exists, stable and apparently dark matter free. The galaxy itself is strange in other ways, is what astronomers call an ultra-diffuse galaxy, about the size of the Milky Way but with 200 times fewer stars. You can literally see through it to galaxies beyond. Its stars are spread so thinly that night skies on any planets there would be almost empty. The galaxy is also remarkably smooth, lacking the spiral arms or central bulge typical of galaxies. It's like a cosmic ghost town. Several theories attempt to explain this dark matter deficiency. One possibility is that NGC 1052 DF2 formed from gas stripped from other galaxies during a high-speed collision. The gas would have already been separated from its dark matter, creating a galaxy born without the usual dark matter component. Another theory suggests the galaxy's dark matter was somehow stripped away by gravitational interactions with a nearby massive elliptical galaxy, NGC 1052. A more radical possibility is that NGC 1052 DF2 formed from the collapse of a massive gas cloud without dark matter involvement. This would require special conditions, perhaps a region where gas pressure and angular momentum balance perfectly, allowing star formation without dark matter's help. Some theorists propose that multiple supernova explosions might have blown out both gas and dark matter, leaving only stars behind. The discovery is controversial. Some astronomers argue the distance measurements might be wrong, which would change the calculated mass. Others suggest the globular cluster velocities might not accurately reflect the galaxy's total mass. But follow-up observations have largely confirmed the original findings. A second galaxy, NGC 1052 DF4, was found with a similar dark matter deficiency, suggesting this isn't a unique anomaly. Ironically, finding a galaxy without dark matter actually strengthens the case for dark matter's existence. If dark matter were just an error in our understanding of gravity, as some alternative theories propose, then all galaxies should show the same apparent dark matter effects. The fact that some galaxies lack these effects suggests dark matter is a real, separate component that can be present or absent. The mystery deepened when astronomers studied the galaxy's globular clusters in detail. These dense star clusters are unusually luminous for their mass, another anomaly. They also seem to be arranged in a remarkably orderly pattern. Unlike the random distribution in most galaxies, it's as if the entire galaxy formed through an unusual process that left multiple signatures of its strange origin. NGC 1052 DF2 forces astronomers to reconsider galaxy formation theories. It shows that galaxies can form and survive without dark matter under certain conditions. This opens new questions. How common are such galaxies? What special conditions allow them to form? And most puzzling, where did all the dark matter go? In 2006, NASA launched a balloon-borne instrument called Arcade to listen to the cosmic radio background, the faint radio whispers from the early universe. Instead of detecting the expected gentle hum, they found a deafening roar. The universe is broadcasting radio waves 6 times stronger than all known sources combined should produce. This cosmic static, dubbed the space roar, is drowning out signals from the first stars and remains one of radio astronomy's biggest mysteries. The discovery was completely unexpected. Astronomers calculated that radio emissions from all known sources, galaxies, quasars, pulsars and other objects, should produce a certain background level of radio noise. Arcade, absolute radiometer for cosmology, astrophysics and diffuse emission, was designed to detect tiny variations in this background that might reveal information about the universe's first stars. Instead, it found a radio background that was far louder than the combined output of every known radio source. The space roar peaks at frequencies between 3 and 90 GHz, with a spectrum that doesn't match any known astrophysical process. It's not coming from our galaxy. The signal is uniform across the sky. It's not from known distant galaxies. There simply aren't enough of them to produce such strong emissions. It's not instrumental error. Multiple experiments have confirmed the excess. The universe is somehow producing 6 times more radio emission than we can account for. This excess radio background has profound implications. The first stars that formed after the Big Bang should have produced a specific radio signature as they ionized the hydrogen around them. This signature would tell us when and how the first stars formed, ending the cosmic dark ages. But the space roar is so loud it completely drowns out these ancient signals. It's like trying to hear a whisper at a rock concert. Several theories attempt to explain the space roar, but none fully succeed. One possibility is a previously unknown population of radio galaxies in the early universe, but these would need to be incredibly numerous and emit radio waves far more efficiently than any galaxies we observe today. The required numbers strain credibility. There would need to be more radio sources than there are stars in all known galaxies. Another theory involves dark matter annihilation. If dark matter particles can annihilate each other, they might produce high-energy particles that emit radio waves as they interact with magnetic fields. But the space roar spectrum doesn't match predictions for dark matter annihilation. The signal is too smooth and extends to frequencies that dark matter scenarios struggle to explain. Some physicists propose exotic explanations. Perhaps the radio waves are fossil remnants from cosmic phase transitions in the early universe. Maybe they're produced by primordial black holes or cosmic strings, hypothetical defects in space-time. One intriguing possibility is that the excess comes from previously undetected clusters of faint dwarf galaxies, but observations haven't found nearly enough to explain the signal. The space roar might be telling us something fundamental about the early universe that we don't understand. Some theorists suggest it could be related to how the first supermassive black holes formed, or to unknown processes during the epoch of reionization when the first stars lit up. It might even indicate that our models of radio emission from galaxies are fundamentally wrong. Attempts to pinpoint the source have been frustrating. The signal appears isotropic, the same in all directions, suggesting either a truly cosmic origin or sources so numerous they're everywhere. High-resolution radio telescopes have failed to resolve it into discrete sources. It's as if the entire universe is glowing in radio waves from some unknown process. The mystery has practical consequences for astronomy. Many experiments designed to study the early universe through radio observations must now contend with this unexpected noise. It's like light pollution for radio telescopes, a cosmic background that obscures the very signals astronomers most want to detect. New techniques and instruments are being developed specifically to peer through the space roar. HD Alton 200283, nicknamed the Methuselah star, presents an embarrassing problem for astronomers. It appears to be older than the universe itself. Initial measurements suggested this star was 16 billion years old, while the universe is only 13.8 billion years old. It's like finding a chicken that's older than the first egg. A logical impossibility that has forced scientists to refine both stellar dating techniques and our understanding of the early universe. This ancient star lies just 190 light-years away in the constellation Libra, practically in our cosmic backyard. It's a subgiant star that has exhausted the hydrogen in its core and begun expanding. What makes it special is its extremely low metallicity. It contains almost no elements heavier than hydrogen and helium. In astronomy, this is a sign of extreme age. Heavy elements are created in stars and spread through space when stars die. So stars with few heavy elements must have formed when the universe was very young. The age paradox emerged from standard stellar evolution models. By measuring the star's temperature, luminosity, and composition, astronomers can calculate how long it's been fusing hydrogen. The initial calculations gave an age of 16 billion years with an uncertainty of 2 billion years. even at the young end of this range, the star would be 14 billion years old, older than the universe's measured age of 13.8 billion years. This cosmic contradiction forced astronomers to scrutinize every assumption. They refined measurements of the star's distance using parallax from the Hubble Space Telescope. They updated models of stellar evolution with better understanding of convection and element diffusion. They reconsidered the effects of the star's unusual composition on its evolution. Each refinement brought the age down, but slowly. The star's composition tells a remarkable story. HD 14.3 has less than 250th the iron content of our Sun. This means it formed from gas that had been enriched by perhaps only 1 or 2 generations of supernovas. It's a near-pristine sample of the early universe, formed when the cosmos was just a few hundred million years old. The star is literally a fossil from the universe's infancy. Recent analysis has resolved most of the age paradox. Using updated stellar evolution models and precise measurements, astronomers now estimate HD 14.0283's age at 13.7 billion years, with an uncertainty of 260 million years. This makes it ancient but not impossible, formed perhaps 100-200 million years after the Big Bang. The star is still one of the oldest known objects in the universe, but no longer older than the universe itself. The controversy highlighted important issues in astronomical dating. Small errors in temperature, composition, or distance measurements can translate to billion-year differences in age estimates. The models used to calculate stellar ages depend on our understanding of nuclear physics, convection, and stellar atmospheres. Any errors in these models accumulate when dealing with such ancient stars. HD 14.283 also raises questions about star formation in the early universe. For such an old star to exist in our neighbourhood suggests that star formation began very quickly after the Big Bang. The first stars must have formed, lived, and died within just a few hundred million years to enrich the gas from which HD 14.283 formed. This rapid early star formation challenges some models of cosmic evolution. The star's current state is also intriguing. Despite its incredible age, HD 14.0283 is still shining steadily. It's in a stable phase of stellar evolution that could last another billion years. When it finally dies, it will do so quietly, expanding into a red giant and then fading as a white dwarf. It lacks the mass for a dramatic supernova ending. Studying HD 14.283 and similar ancient stars helps astronomers understand conditions in the early universe. These stars are time capsules, preserving information about the composition and conditions of space when the universe was young. They're the closest we can come to directly observing the universe's earliest epochs without looking billions of light years into space. HD 131399AB makes the fictional Tatooine look boring. While Luke Skywalker watched twin suns set on his desert world, anyone standing on HD 131399AB would see 3 suns dancing across the sky in a cosmic ballet that lasts 550 Earth years. This giant planet, located 340 light-years away, orbits in one of the most complex and precarious celestial arrangements ever discovered, a gravitational juggling act that shouldn't be stable, yet somehow is. The planet itself is a giant, about 4 times the mass of Jupiter, orbiting the largest of 3 stars in the system. This primary star, HD 1339A, is about twice the mass of our Sun. The other 2 stars, B and C, orbit each other like a binary pair, and this pair orbits star A at a much greater distance. The planet somehow threads the gravitational needle, maintaining a stable orbit around star A while the BC pair tugs at it from afar. For about half of the planet's 550-year orbit, all 3 stars appear in the sky simultaneously. As the planet moves through its orbit and the stellar pairs dance around each other, the view changes dramatically. Sometimes the stars are close together in the sky, other times spread apart. For about 1/4 of the orbit, when the BC pair is on the opposite side of star A, the planet experiences constant daylight. As one sun sets, another rises. The discovery in 2016 using direct imaging challenged astronomers' understanding of planetary orbital dynamics. In most triple-star systems, the competing gravitational forces create chaotic zones where planets can't maintain stable orbits. The stellar dance creates constantly shifting gravitational fields that should fling planets out of the system or send them crashing into one of the stars. HD 131399AB exists in defiance of these expectations. Computer simulations reveal just how precarious the planet's situation is. Its orbit takes it about 80 AU from star A, twice the distance of Pluto from our Sun. The BC binary pair orbits at about 300-400 AU from star A. This puts the planet in a narrow zone of stability. If it were closer to star A, the BC pair's influence would be too weak to matter. If it were farther out, their gravity would destabilize its orbit. The planet's survival depends on orbital resonances, precise mathematical relationships between the orbital periods of the planet and the stellar pairs. Like a child timing their jumps on a swing, the planet's orbit is synchronized with the stellar motions in a way that minimizes disruptive gravitational encounters. This cosmic choreography must have been established early in the system's formation and maintained for millions of years. Temperature variations on HD 131399 would be unlike anything in our solar system. The planet receives light and heat from 3 different sources, each varying in intensity as the geometric configuration changes. Climate models suggest the planet might have seasons lasting centuries, with temperature patterns shifting as different stars dominate the sky at different times. The complexity makes Earth's simple summer-winter cycle seem quaint. The planet's atmosphere, observed through infrared spectroscopy, contains water vapour and methane. At about 580 deg, it's too hot for life as we know it, but cool for a giant exoplanet. The 3 stars likely create complex atmospheric dynamics, with winds and weather patterns driven by the shifting stellar radiation. Imagine jet streams that reverse direction over centuries as the dominant heat source moves across the sky. Formation scenarios for HD 131399AB are highly debated. One possibility is that it formed around star A normally and survived the later capture of the BC pair. Another is that it formed farther out and migrated inward to its current position. Some models suggest it might have formed around the BC pair and been captured by star A. Each scenario requires a precise series of unlikely events, making this planet extraordinarily rare. The discovery method itself was remarkable. Most exoplanets are found through indirect methods like transits or radial velocity measurements. HD 131399AB was directly imaged, its light separated from the glare of its 3 parent stars. This was only possible because the planet is young, about 16 million years old, and still glowing from the heat of its formation. In infrared light it shines brightly enough to be distinguished from its stellar parents. Recent observations have raised questions about the planet's long-term stability. Some models suggest its orbit might be chaotic over million-year timescales, with the planet eventually ejected from the system or crashing into one of the stars. Other models find stable configurations that could last billions of years. The planet exists at the edge of what's gravitationally possible, making its future uncertain. On October 15, 1991, a cosmic ray detector in Utah registered something that shouldn't exist. A single subatomic particle, likely a proton, slammed into Earth's atmosphere with an energy of 3.2 x 1020 electron volts. That's 40 million times more energetic than particles in the Large Hadron Collider. Scientists dubbed it the "oh my god" particle, because no known process in the universe should be able to accelerate a particle to such mind-bending energies. To understand how extreme this is, consider that this single proton carried the kinetic energy of a baseball pitched at 100 km per hour. But a baseball contains about 10 to the 26 particles. This cosmic ray packed all that energy into a single subatomic particle. making it the highest energy particle ever detected. It was travelling at 99.99999999 faster for 1% the speed of light, so close to light speed that it would take 215,000 years to fall 1 metre behind a photon in a race. The detection came from the Fly's Eye cosmic ray detector, an array of mirrors and photomultiplier tubes in the Utah desert. When the particle hit Earth's atmosphere, it created an extensive air shower, a cascade of billions of secondary particles that spread across kilometres. The shower's size and intensity revealed the primary particle's unprecedented energy. Scientists initially thought their instruments had malfunctioned. What makes the oh my god particle so puzzling is that it shouldn't have been able to reach Earth. At such extreme energies, protons interact with the cosmic microwave background radiation that fills all of space. This interaction, called the Giesecke cutoff, should limit cosmic ray energies to about 5 × 1019 electron volts. Any particle more energetic would lose energy through collisions with CMB photons within about 160 million light-years. The oh my god particle had 6 times this theoretical maximum energy. The particle's origin remains unknown. Whatever accelerated it must be one of the most extreme environments in the universe. Candidates include supermassive black holes in active galactic nuclei, gamma-ray bursts, or colliding galaxies. But even these cosmic powerhouses struggle to explain such energies. Some theories invoke multiple acceleration stages or magnetic field configurations we don't yet understand. From the particle's perspective, the universe looked completely different due to extreme relativistic effects. Its journey to Earth, which took millions of years in our reference frame, lasted only about 20 seconds in the particle's frame. The cosmic microwave background, normally at 2.7 Kelvin, appeared blue-shifted to gamma-ray energies. The particle saw the universe compressed into a thin disk ahead of it, with all of cosmic history playing out in fast-forward. The oh my god particle wasn't a complete anomaly. Since its detection, about 100 more ultra-high energy cosmic rays above 10⁻20 electron volts have been observed. The Pierre Auger Observatory in Argentina and the Telescope Array in Utah continue to detect these extreme particles, though none have matched the original's energy. Each detection provides clues about the universe's most violent processes. One proposed explanation involves hypothetical super-heavy dark matter particles. If dark matter particles with masses of 1024 electron volts exist, their decay could produce the observed ultra-high energy cosmic rays. This would sidestep the Giesecke cutoff because the particles would originate nearby. But no other evidence for such super-heavy dark matter exists, making this explanation controversial. The particle's impact on Earth's atmosphere created a shower of secondary particles covering 18 square kilometres. If you had been standing in the shower's path, about 100 billion particles would have passed through your body in a few microseconds. Despite the enormous primary energy, the shower particles were harmless. The energy was spread among so many particles that each carried little danger. The mystery deepened when astronomers tried to trace the particle's path back to its source. Its arrival direction didn't point to any obvious cosmic accelerator. No nearby active galactic nucleus, no recent gamma-ray burst, no special astronomical object lies along its trajectory. Either the source is invisible to our telescopes, or magnetic fields bent the particle's path so much that backtracing is impossible. RZ Piscium can't decide whether it wants to be visible or not. This erratic star, located 550 light-years away, undergoes unpredictable dimming events, where it fades by a factor of 10 for days or weeks at a time. Unlike regular variable stars that follow predictable patterns, RZ Piscium flickers chaotically, sometimes dimming multiple times per year, sometimes staying bright for years. It's as if someone is randomly flipping a cosmic dimmer switch. The star itself appears to be young, perhaps only 30–50 million years old, but shows characteristics usually seen in much older stars. It's surrounded by a disk of warm dust that glows brightly in infrared light, far more dust than a star this age should have. The dust temperature, about 500 Kelvin, suggested orbits close to the star. But here's the puzzle. Young stars should have cold dust far from the star, while old stars might have warm dust from ground-up asteroids. RZ Piscium has the wrong type of dust for its age. When RZ Piscium dims, it doesn't just get fainter, its light changes colour, becoming redder. This indicates that something is passing in front of the star and blocking its light, not that the star itself is changing brightness. But unlike exoplanet transits that last hours and repeat regularly, these dimming events are irregular and prolonged. Whatever is blocking the light is huge, extended, and chaotic. The leading theory involves planetary destruction on a massive scale. Ars Piscium might be caught in the act of destroying one or more planets in its system. If a planet's orbit became unstable, tidal forces could tear it apart, creating vast clouds of debris. These debris clouds would orbit chaotically, occasionally passing between us and the star, causing the observed dimming. It would be planetary murder in slow motion. X-ray observations support the catastrophic scenario. The star emits X-rays at levels 1,000 times higher than our Sun, indicating extreme magnetic activity or accretion of material onto the star. If planetary debris is falling onto RZ Piscium, the infalling material would heat up and emit X-rays. The star might literally be feeding on the remains of its planets. Another possibility involves massive collisions in an asteroid belt or between planetary embryos. If RZ Piscium's system is undergoing late-stage planet formation, giant impacts could create debris clouds that cause the dimming. But the frequency and scale of dimming events would require almost continuous collisions, which seems unlikely. The dust production rate is enormous, equivalent to grinding up Earth-sized bodies every few years. Spectroscopic observations reveal another clue: lithium absorption lines that shouldn't be there. Lithium is destroyed in stellar interiors, so stars RZ Piscium's age shouldn't show strong lithium features. The lithium might come from accreted planetary material, or indicate the star is younger than thought. This adds another layer to the mystery. Is the star young and destroying primordial planets, or older and grinding up mature worlds? The dust around RZ Piscium isn't distributed uniformly. Infrared observations show it's clumped and possibly confined to specific orbital regions. This suggests we're not seeing a smooth disk, but a chaotic mess of debris streams, dust clouds, and possibly surviving planets stirring up the material. The geometry changes over time, which could explain the irregular dimming pattern. Some astronomers propose we're witnessing a rare phase of planetary system evolution. Perhaps all stars go through a period of planetary destruction and reorganisation, but it happens so quickly we rarely catch it in action. RZ Piscium might be showing us what our own solar system looked like during the late heavy bombardment, when planet migration caused system-wide chaos. Recent observations have detected gas as well as dust around the star. The presence of carbon monoxide and other molecules suggests ongoing collisions that vaporise icy bodies. The gas should dissipate quickly under stellar radiation, so its presence indicates continuous replenishment. Something is actively destroying icy objects in the RZ Piscium system right now. K2-137b redefines the concept of a year. This ultra-short period planet, slightly smaller than Earth, races around its star in just 16.3 hours. By the time you've had a good night's sleep, woken up, and gone through your morning routine, K2-137b has completed an entire orbit. It's the planetary equivalent of a Formula One car on a cosmic racetrack, pushing the boundaries of how close a planet can orbit without being destroyed. The planet orbits just 1.3 million kilometres from its star. That's less than the diameter of the Sun itself. At this distance, K2-137b is practically skimming its star's surface. The planet is so close that tidal forces have likely locked its rotation, meaning one side faces eternal daylight while the other endures eternal night. Surface temperatures on the day side probably exceed 2000 degrees Celsius, hot enough to vaporize rock. The discovery required incredibly precise timing. The planet was found using the transit method, where it passes in front of its star as seen from Earth. but with such a short orbit, these transits happen every 16 hours and last only about 45 minutes. Missing just one day of observations means missing multiple transits. Automated algorithms scanning data from the K2 mission flagged this rapid-fire dimming pattern. What makes K2 137b extraordinary is that it exists at all. Planets this close to their stars face numerous threats. Stellar radiation pressure tries to blow away their atmospheres. Tidal forces from the star's gravity try to tear them apart. The star's magnetic field induces currents that heat the planet's interior. By all rights, K2 137b should have been destroyed long ago, yet it persists in its hellish orbit. The planet's survival might depend on its composition. Models suggest K2 137b could be the exposed core of a gas giant that lost its atmosphere. Made primarily of iron and rock, it would be dense enough to resist tidal destruction. Think of it as a cosmic cannonball, small, dense, and incredibly resistant to the forces trying to destroy it. Some call these objects Chthonian planets, after the Greek deities of the underworld. The orbital velocity is staggering. K2 137b travels at approximately 230 km per second to maintain its orbit. That's fast enough to circle Earth in under 3 minutes. The planet experiences accelerations that would flatten any known material. If you could somehow stand on its surface, you'd weigh significantly less on the side facing the star due to the partial cancellation of gravity by centrifugal force. Atmospheric retention is impossible under these conditions. Any gases would be stripped away by stellar wind within days. The day side might have lakes or even oceans of molten metal, with iron and nickel flowing like water. The night side could be cold enough for these metals to freeze, creating a landscape of metallic ice. Between these extremes, at the Terminator line, conditions would be violently unstable. K2 137b belongs to a growing class of ultra-short-period planets, worlds that complete orbits in less than a day. About 50 such planets are known, and they're teaching us about planetary physics under extreme conditions. They represent the inner edge of where planets can exist. Any closer, and they'd spiral into their stars or be torn apart by tidal forces. The planet's origin is debated. It couldn't have formed where it is now. The protoplanetary disk would have been too hot and turbulent so close to the star. It must have migrated inward from a more distant orbit. But what drove this death spiral? Gravitational interactions with other planets? Drag from the protoplanetary disk? The mechanism must have been precise enough to park the planet just outside the destruction zone. Studying K2 137b helps astronomers understand star-planet interactions at their most extreme. The planet likely drives waves in its star's atmosphere, creates magnetic reconnection events, and might even influence the star's rotation. It's not just a planet orbiting a star. It's a coupled system where each component significantly affects the other. IPTF-14HL refuses to die like a normal star. Discovered in 2014, this supernova appeared to be a typical stellar explosion at first, but instead of fading away over a few months as supernovas should, IPTF-Ls kept shining for over 600 days. Even stranger, archival data revealed the same star had exploded once before in 1954. It's a stellar zombie that survived its own death, challenging our fundamental understanding of how stars die. When massive stars exhaust their nuclear fuel, they undergo core collapse and explode as supernovas, completely destroying themselves in the process. The explosion should be final. There's not supposed to be an encore, but IPTF-14HL has exploded at least twice and might still be intact. Over the 600 days of observations, it brightened and dimmed at least 5 times, each peak resembling a new explosion. The total energy released was staggering. Normal supernovas release about 1051 ergs of energy. IPTF-14HL released more than 10 times this amount, spread over its multiple peaks. The star ejected more than 50 times the mass of our Sun in material, far more than most stars contain. these numbers don't add up unless the progenitor star was extraordinarily massive, perhaps 100 times the Sun's mass or more. Spectroscopic analysis deepened the mystery. The explosion showed signatures of hydrogen, unusual for a star massive enough to produce such an energetic supernova. The expansion velocity of the ejected material was also strange, remaining constant at about 4,000 kilons instead of slowing down as expected. Temperature measurements revealed another anomaly. The explosion maintained a steady temperature for months, as if powered by a continuous energy source. One explanation involves a theoretical phenomenon called a pulsational pair instability supernova. In extremely massive stars, the core can become so hot that photons spontaneously create electron-positron pairs. This suddenly reduces radiation pressure, causing a partial collapse and explosion that doesn't destroy the star. The star can undergo multiple such pulses over years or decades before finally exploding completely. But even this exotic mechanism struggles to explain IPTF 14HLLs. The energy output is too high, the duration too long, and the 1954 explosion predates the recent one by 60 years, much longer than models predict between pulses. Some theorists propose we're seeing an entirely new type of stellar death, one that occurs only in the most massive stars under specific conditions. Another possibility is that IPTF 40HLS isn't a single star, but a binary system undergoing complex interactions. If two massive stars were merging or exchanging material, it might create the appearance of multiple explosions. But the spectral signatures don't clearly support this scenario. The light curve and spectrum are more consistent with a single, albeit very unusual object. The star's location provides few clues. It sits in a small dwarf galaxy about 500 million light-years away. The host galaxy's low metallicity suggests IPTF 40 Stacels formed from relatively pristine gas, which might have allowed it to grow to extraordinary size. In the early universe, such monster stars might have been more common, making IPTF 14 RCLs a possible relic of ancient stellar populations. The implications are profound. If stars can explode multiple times before dying, it changes our understanding of stellar evolution, element production, and galaxy chemical enrichment. Each explosion spreads heavy elements into space, contributing to the next generation of stars. Multiple explosions from the same star would alter these calculations significantly. Continued monitoring has shown the storiesforsleep is finally fading, but slowly. The star, or its remnant, is still visible years after discovery, glowing with the light of radioactive decay. Whether it will explode again remains unknown. Astronomers continue to watch, waiting to see if this zombie star has another resurrection in store. While black holes are cosmic vacuum cleaners that swallow everything, Einstein's equations also permit their opposite: white holes that spew matter and energy outward. Nothing can enter a white hole, just as nothing can escape a black hole. They would appear as brilliant sources of light and matter erupting from a point in space. While no white hole has been observed, they remain a tantalizing theoretical possibility that could explain some of the universe's most puzzling phenomena. The mathematics of white holes emerges naturally from general relativity. If you take the equations describing a black hole and reverse time, you get a white hole. Where a black hole has an event horizon that things fall through never to return, a white hole has an anti-horizon that things emerge from but can never enter. It's like playing a video of matter falling into a black hole in reverse. The properties of white holes would be bizarre. Imagine approaching one in a spacecraft. As you get closer, you'd encounter matter and radiation streaming outward with increasing intensity. But no matter how powerful your engines, you could never reach the white hole itself. The outflowing material would push you away with ever greater force. Even light aimed at a white hole would be reflected, making it impossible to probe directly. White holes face a fundamental problem. They violate the second law of thermodynamics, which says entropy must increase over time. A white hole would spontaneously decrease entropy by ejecting organized matter and energy from a point source. This is why physicists generally believe white holes can't form naturally in our universe, but they might have existed in the extreme conditions of the very early universe. One intriguing possibility connects white holes to the Big Bang itself. Some cosmologists propose that our universe began as a white hole, a point from which space, time, matter, and energy emerged and can never return. In this view, the Big Bang singularity is mathematically equivalent to a white hole singularity. We're living inside the expansion of the ultimate white hole. Another connection involves black holes themselves. Some theories suggest that matter falling into a black hole might emerge from a white hole in another universe, or another region of our universe. The black hole and white hole would be connected by a wormhole, creating a cosmic recycling system. This remains highly speculative, as we have no evidence for wormholes or connections between black and white holes. Gamma-ray bursts, the universe's most powerful explosions, have been proposed as potential white hole signatures. These brief, intense flashes of radiation release enormous energy from point sources. While most are explained by collapsing stars or merging neutron stars, some gamma-ray bursts have properties that are difficult to explain conventionally. Could they be white holes briefly erupting into existence? The search for white holes faces observational challenges. A white hole would be incredibly bright and obvious, unless it formed in empty space with nothing to eject. A naked white hole with no surrounding matter might be nearly impossible to detect. It would gravitationally repel anything that approached, creating an empty bubble around itself. Some physicists propose that white holes might be created in particle accelerators or in the extreme conditions near black holes. If microscopic white holes could form, they would immediately explode in a burst of Hawking radiation. The Large Hadron Collider hasn't detected any such events, placing limits on white hole formation in current experiments. Recent work in loop quantum gravity, an attempt to unify quantum mechanics and general relativity, suggests a fascinating possibility. Black holes might transform into white holes through quantum effects. After a black hole forms and ages, quantum gravity effects could cause it to bounce, transforming it into a white hole that ejects everything the black hole consumed. This process would take longer than the current age of the universe for stellar mass black holes. Kepler 13ab experiences weather that would be a dermatologist's dream. On this massive hot Jupiter, titanium oxide, one of the active ingredients in sunscreen, snows out of the atmosphere on the planet's permanent night side. This creates a bizarre meteorological cycle where sunscreen literally falls from the sky, only to vaporize again if it ever reaches the scorching day side. The planet orbits so close to its star that it's tidally locked, with permanent day and night sides. The day side reaches temperatures of 3000 Ulk, hot enough to vaporize virtually any known substance. But the night side, while still hellishly hot at around 2500 Ulk, is cool enough for titanium oxide to condense out of the gaseous atmosphere and fall as snow. It's a precipitation cycle, but with temperatures that would instantly incinerate any earthly substance. This sunscreen snow was discovered through a peculiar absence. Hot Jupiters typically show titanium oxide in their upper atmospheres, where it absorbs light and creates a temperature inversion, making the upper atmosphere hotter than lower layers. But Kepler 13ab's day side showed no such signature. Scientists realized the titanium oxide was missing because it was constantly being removed from the atmosphere, snowing out on the night side. The mechanism is fascinatingly complex. On the day side, titanium oxide exists as a gas, mixed throughout the atmosphere. Powerful winds, driven by the extreme temperature difference between day and night, carry this gas to the cooler night side at speeds exceeding 5,000 km/h. As the gas cools, titanium oxide molecules cluster together, forming tiny crystalline particles that fall as snow. But here's where it gets strange. Kepler 13ab is so massive, about 6 times Jupiter's mass, that its gravity prevents the titanium oxide snow from being recycled back to the day side. On smaller hot Jupiters, atmospheric circulation would carry the condensed particles back to the day side where they'd vaporize again. But Kepler-13b's powerful gravity traps the snow, creating a one-way precipitation system. The implications are profound for planetary atmospheric dynamics. Without titanium oxide in its upper atmosphere, Kepler-13b's day side lacks the usual temperature inversion. Instead, it gets cooler with altitude, more like Earth's troposphere. This fundamentally changes how energy moves through the atmosphere and affects everything from wind patterns to chemical reactions. The snow itself would be unlike anything on Earth. Titanium oxide crystals falling through a 2500 Descent atmosphere would glow with their own heat. The night side would be illuminated by a constant rain of glowing particles, creating an eerie twilight even in the absence of starlight. The particles would be microscopic, but their collective effect would be visible as a shimmering curtain of light. Ground-level effects would be even more extreme. If the planet has a solid surface, which is uncertain for such a massive world, it might be covered in drifts of titanium oxide snow on the night side. These wouldn't be white, fluffy drifts, but likely dark, dense accumulations of metallic oxide particles. The boundary between day and night would be marked by a sharp transition from bare, superheated rock to snow-covered terrain. The discovery required sophisticated atmospheric modelling. Scientists used the Spitzer Space Telescope to measure the planet's thermal emission at different orbital phases. By analysing how the brightness changed as the planet orbited, they could map temperature variations and chemical compositions. The absence of the expected titanium oxide signature on the day side was the crucial clue. This process might not be unique to Kepler-13b. Other ultra-hot Jupiters with similar masses might experience comparable metal snow. Iron, aluminum oxide, and other refractory materials could condense on night sides, creating a whole new class of precipitation unknown in our solar system. Each would have its own condensation temperature and atmospheric effects. CFB-DSIR 2149-0403 challenges our notion of what a star can be. With a surface temperature of just 100 Crist, cooler than boiling water and barely warmer than a hot cup of coffee, this brown dwarf exists at the boundary between stars and planets. Yet deep in its core, hydrogen fusion still occurs, making it technically a star despite being cool enough to theoretically touch, if you could somehow survive the gravity. This cosmic lightweight has a mass between 4 and 7 times that of Jupiter, placing it right at the threshold for stellar fusion. Below about 13 Jupiter masses, objects can't even fuse deuterium and are considered planets. Above 80 Jupiter masses, they become proper stars. Brown dwarfs like CFB-DSIR 2149-0443 occupy the strange middle ground, massive enough for limited fusion but not massive enough to sustain it long term. The fusion occurring in its core is barely there. Unlike our Sun, which fuses hydrogen into helium at 15 million degrees, this brown dwarf manages only sporadic deuterium fusion and extremely slow hydrogen fusion through quantum tunneling. The energy output is pathetic by stellar standards. It shines with less than 0.0001% of the Sun's luminosity. You'd receive more heat standing next to a campfire than orbiting this star. What makes CFB-DSIR 2149-0403 even more unusual is that it appears to be a rogue, drifting through space without a parent star. It's part of the AB Doradus moving group, a collection of stars that formed together about 120 million years ago. But while its siblings orbit in normal stellar systems, this brown dwarf wanders alone through the darkness, a failed star expelled from its birthplace. The surface conditions would be utterly alien. At 100 degrees C, water could exist as vapour in the atmosphere, and complex chemistry becomes possible. The atmosphere likely contains methane, water vapour, and possibly even more complex hydrocarbons. Iron and silicate clouds might form in the upper atmosphere, creating weather patterns unlike anything in our solar system. Rain wouldn't be water, but perhaps liquid iron droplets. Detecting such a cool object required infrared telescopes. In visible light, CFBDS-IR 20-149 0403 is essentially invisible, emitting less light than a candle, but in the infrared, it glows faintly with its own heat. The Canada-France Brown Dwarf Survey found it by looking for objects with extremely red colours. So red they're basically black in visible light but detectable in the infrared. The physics of such cool stars is exotic. At these temperatures, molecules that would be destroyed in normal stars can survive. The atmosphere might contain not just simple molecules but complex compounds, possibly even organic molecules. Some scientists speculate that the upper atmospheres of brown dwarfs could host prebiotic chemistry, though the gravity and lack of solid surfaces make this largely academic. Time moves differently for brown dwarfs. While our Sun will exhaust its hydrogen in 10 billion years, CFBDER 2149-0403 will continue its feeble fusion for trillions of years. It will slowly cool and fade but never die dramatically. In the far future, when all bright stars have burned out, brown dwarfs will be among the last objects shining in a darkened universe. The boundary between planet and star blurs with objects like this. If CFBDS-IR 20-1490403 were orbiting a star, we'd probably call it a planet despite its fusion. As a free-floating object, it's classified as a substellar object or brown dwarf. The distinction becomes somewhat philosophical. Is fusion alone enough to make something a star, or do other factors matter? Recent studies suggest brown dwarfs might be incredibly common. For every normal star, there might be several failed stars lurking in the darkness. The galaxy could be full of these coffee-temperature stars drifting unseen and barely warming the cosmos with their feeble glow. The shape of the universe itself remains one of cosmology's deepest mysteries. While we often imagine infinite space stretching in all directions, recent data suggests the universe might be curved in on itself like a cosmic donut, what mathematicians call a three-torus. In this scenario, travelling far enough in any direction would eventually bring you back to where you started, like a cosmic version of the video game Pac-Man. The evidence comes from subtle patterns in the cosmic microwave background, CMB, the afterglow of the Big Bang. If the universe is truly infinite, we'd expect the CMB's temperature fluctuations to be random at all scales, but some analyses have found hints of matching patterns on opposite sides of the sky, as if we're seeing the same regions from different directions. It's like looking in parallel mirrors and seeing infinite reflections of the same space. In a toroidal universe, space wraps around in all three dimensions. Travel far enough up and you'd emerge from below. Go far enough east and you'd return from the west. But this isn't simply a sphere, it's more complex. A three-torus is the three-dimensional equivalent of a donut surface, where space connects to itself in ways our brains struggle to visualize. The size matters crucially. If the universe is a torus, it must be larger than the observable universe, at least 93 billion light-years across, or we'd see obvious repeating patterns. Light from the same galaxy would reach us from multiple directions, creating a hall of mirrors effect. The fact that we don't see obvious duplicates means that if the universe is finite, it's still enormous. This topology would have profound implications. In an infinite universe somewhere far enough away, random quantum fluctuations would create exact copies of everything, including you. But in a finite toroidal universe, there's only so much space and matter. Every atom would be unique. The universe would be vast but bounded, like the surface of Earth but in 3 dimensions. The curvature measurements are contentious. The Planck satellite measured the universe as flat to within 0.4% accuracy, suggesting infinite space. But a 2019 reanalysis of the same data found hints of positive curvature, implying a closed universe. The disagreement highlights how difficult it is to measure the shape of something we're inside of. It's like an ant, trying to determine if it's on a basketball or an infinite plane. Different topologies create different patterns in the CMB. A toroidal universe would create specific symmetries in the temperature fluctuations. Scientists have searched for these circles in the sky, matching patterns that would indicate space folding back on itself. Some claim to have found them, others argue the patterns are statistical flukes. The debate continues with each new dataset. The physics of a toroidal universe would be subtly different. Gravity waves would propagate around the universe and interfere with themselves. Very long wavelength radiation might not fit properly, like trying to wrap gift paper around an oddly shaped box. These effects would be tiny, but potentially detectable with sensitive enough instruments. String theory naturally accommodates toroidal universes. In many string theory models, extra dimensions are compactified into tiny tori. Our three-dimensional space might similarly be a giant torus, just one we can't see the edges of. This connects the larger scales of the universe to the smallest, with topology playing a crucial role at both extremes. The philosophical implications are staggering. In a toroidal universe, you could theoretically return to your starting point by travelling in a straight line, though it would take longer than the universe's current age. Every point would be both unique and connected to every other point through the topology. The universe would be simultaneously finite and unbounded, limited yet without edge. Proxima Centauri b exists in perpetual twilight. Our nearest exoplanet neighbour, just 4.2 light-years away, is tidally locked to its red dwarf star. One hemisphere basks in eternal day, while the other freezes in endless night. But the most interesting region might be the terminator, the twilight zone between day and night where temperatures could be just right for liquid water and possibly life. The planet orbits Proxima Centauri every 11.2 days at just 5% of Earth's distance from the Sun. At this proximity, tidal forces have synchronized its rotation with its orbit, the same way our Moon always shows the same face to Earth. But unlike the Moon, which experiences day and night as it orbits Earth, Proxima b's sun never moves in its sky. On the day side, the red sun hangs motionless, forever fixed at the same altitude. Climate models reveal a world of extremes. The subsolar point, where the star appears directly overhead, experiences temperatures around 30 degrees, comfortable by Earth standards. But this warmth comes from a red star that bathes the landscape in crimson light. Plants evolving here might be black to absorb the infrared heavy radiation. The eternal noon creates a permanent high-pressure zone, with air constantly rising and flowing toward the night side. The night side tells a different story. Without any starlight, temperatures plummet to 90 diamestus, or colder. Any atmosphere would freeze out here, falling as snow or frost. Carbon dioxide would form glaciers. Water ice would be harder than granite. This frozen hemisphere would be darker than any night on Earth, lit only by the faint glow of the galaxy, and perhaps auroras caused by stellar flares. Between these extremes lies the terminator zone, a ring around the planet where the star sits permanently on the horizon. Here, temperatures might hover around descent, allowing liquid water to exist. This twilight realm would experience eternal sunrise or sunset, with long shadows and reddish light painting the landscape. If life exists on Proxima b, this might be its refuge. The atmospheric circulation would be unlike anything on Earth. Hot air from the day side would rise and flow toward the night side, where it would cool and descend. This would create a planet-girdling circulation pattern, with fierce winds at high altitudes and return flows at the surface. The terminator zone might experience constant storms as hot and cold air masses clash. Water presents a particular challenge. Any water on the day side would evaporate and be carried to the night side, where it would freeze out. Over time, all water might become trapped in a massive ice cap on the night hemisphere, but if the atmosphere is thick enough, it could transport enough heat to keep some water liquid. Ocean currents, if they exist, would flow from day to night, potentially preventing complete freezing. Proxima Centauri itself adds complications. Red dwarf stars are prone to massive flares that can increase their brightness by factors of hundreds in minutes. For Proxima b, these flares would be catastrophic events. The day side would be scorched by radiation, while the night side might briefly experience something like dawn. Any life would need to cope with these periodic sterilization events. The planet's potential habitability depends critically on unknowns like atmospheric thickness and composition. A thick atmosphere could redistribute heat, moderating the temperature extremes, but too thick, and you get a runaway greenhouse effect. Too thin, and the atmosphere freezes out on the night side. The sweet spot for habitability might be narrow. Recent observations have constrained some properties. The planet is roughly Earth-sized, with a minimum mass 1.3 times Earth's. It receives about 65% of the energy Earth gets from the Sun, but in the form of infrared rather than visible light. No atmosphere has been detected yet, but that doesn't mean one doesn't exist. It's simply at the limit of current detection methods. Achernar spins so fast it has squashed itself into a cosmic pancake. This bright star in the constellation Eridanus rotates at 290 kilometers per second at its equator, so fast that centrifugal force has flattened it into an oblate spheroid with an equatorial diameter 56% larger than its polar diameter. It's the most distorted star visible to the naked eye, a cosmic demonstration of what happens when rotation pushes against gravity's desire for spherical perfection. The physics are straightforward but extreme. Any rotating body experiences centrifugal force that opposes gravity. Earth is slightly flattened for this reason, but only by 0.3%. Achernar rotates at 95% of its breakup velocity, the speed at which centrifugal force would overcome gravity and tear the star apart. Just a little faster, and material at the equator would fly off into space. This extreme rotation creates bizarre conditions. The equatorial regions experience significantly lower effective gravity than the poles. This makes the equator cooler and less dense than the poles, a phenomenon called gravity darkening. Temperature variations across the star's surface can exceed 4,000 degrees. The poles glow white-hot while the equator is merely red-hot, creating a star with built-in climate zones. The shape distortion is so extreme that Achernar doesn't even look like a star from most angles. Viewed from above its poles, it appears round and normal, but from the side it looks like a bright ellipse, almost twice as wide as it is tall. The star's apparent brightness and colour change depending on viewing angle, making it a challenge for astronomers to study. How did Achernar reach such extreme rotation? Stars are born spinning, inheriting angular momentum from their parent gas clouds. As they contract during formation, they spin faster, like ice skaters pulling in their arms. But most stars have mechanisms to shed angular momentum: stellar winds, magnetic fields, or planet formation. Achernar somehow retained most of its primordial spin. The rapid rotation affects everything about the star. Its magnetic field is likely complex and tangled. Stellar winds would be stronger at the poles where gravity is higher. The internal circulation of gas would follow patterns impossible in slowly rotating stars. Even nuclear fusion rates might vary between equator and poles due to the different pressures and temperatures. Achernar isn't alone in its distortion. Other fast rotators like Altair and Vega show similar but less extreme flattening. The phenomenon seems most common in hot, massive stars that have weak magnetic fields and thus less magnetic braking. These stars live fast and die young. Their rapid rotation is partly a consequence of their short lifetimes not giving them time to slow down. Recent interferometric observations have revealed even more complexity. Achernar appears to have a disk or shell of material around its equator, possibly gas thrown off by the rapid rotation, or trapped in orbit by the complex gravitational field. This makes it not just a flattened star, but potentially a star in the process of losing mass from its equator. The interior structure must be exotic. In a normal star, heat flows from the hot core to the cooler surface relatively uniformly. In Achernar, the temperature and pressure gradients are asymmetric. The core itself might be oblate. Convection patterns would be dramatically different from spherical stars. It's a natural laboratory for testing stellar physics under extreme conditions. Achernar challenges stellar evolution models. How does fusion proceed in such a distorted star? How does it age compared to spherical stars? Will it eventually slow down, or will it maintain its pancake shape until death? These questions push astronomers to develop more sophisticated models that account for rapid rotation. The universe has a skeleton. Called the cosmic web, it's a vast network of dark matter filaments that connects every galaxy to every other galaxy across billions of light years. These invisible threads channel matter and energy throughout the cosmos, creating a structure remarkably similar to neural networks in the brain or the root systems of forests. We live inside the universe's own nervous system. The cosmic web emerged from tiny quantum fluctuations in the infant universe. Regions slightly denser than average attracted more matter through gravity, while less dense regions emptied out. Over billions of years, this process created a foam-like structure. Dense nodes where galaxy clusters form, connected by filaments where galaxies align like pearls on strings, surrounding vast empty voids. Dark matter forms the scaffolding of this web. Invisible and interacting only through gravity, dark matter outweighs normal matter 5-1. It collapsed first in the early universe, creating gravitational channels that guided normal matter into the patterns we see today. Galaxies didn't form randomly scattered through space. They formed along these pre-existing dark matter highways. The filaments themselves are stupendous. A typical filament stretches hundreds of millions of light years, containing millions of galaxies. The largest known filament, the Hercules Corona Borealis Great Wall, spans 10 billion light years. These aren't solid structures, but rivers of galaxies flowing through space, bound together by mutual gravitation and embedded in halos of dark matter. Recent observations have made the invisible visible. By studying how light from distant galaxies is distorted by gravitational lensing, astronomers can map dark matter distribution. The results reveal filaments everywhere, connecting galaxy clusters like a three-dimensional spider web. Some filaments are thick and galaxy-rich, others are tenuous threads with just a few galaxies strung along their length. The web is dynamic. Galaxies stream along filaments toward massive clusters, like water flowing down cosmic drains. Where filaments meet, galaxy clusters grow ever larger. Computer simulations show this flow accelerating over time, as gravity pulls matter from voids into filaments and from filaments into nodes. The universe is actively organizing itself into an ever more connected network. Gas flows along these cosmic highways too. Recent observations detected hot gas in filaments through its X-ray emission and the shadows it casts on the cosmic microwave background. This intergalactic medium contains more normal matter than all the galaxies combined. It's heated to millions of degrees by shock waves as it falls into the gravitational wells of the web. The resemblance to neural networks isn't just visual. Mathematical analyses show the cosmic web and brain networks share similar statistical properties. Both are small world networks, where any two nodes connect through just a few steps. Both show similar scaling laws and information flow patterns. The universe seems to organize matter using principles similar to those governing complex biological systems. Our own galaxy's position in the web influences its evolution. The Milky Way sits in a relatively quiet filament, streaming toward the Virgo cluster along with other local group galaxies. This motion affects star formation rates, galaxy interactions, and even the orbits of satellite galaxies. We're not isolated in space, but embedded in a vast network of gravitational relationships. The cosmic web challenges our perception of emptiness. What looks like vacant space between galaxies is actually crisscrossed by invisible threads of dark matter and hot gas. A true map of the universe would show matter everywhere, just concentrated in patterns too large and faint for human eyes to perceive. Empty space is an illusion created by our limited vision. HAT P7b takes the concept of precious stones to cosmic extremes. This scorching hot Jupiter, 1,000 light-years from Earth, has clouds made of corundum, the same mineral that forms rubies and sapphires on Earth. These clouds don't produce gentle rain, but violent storms of liquid aluminum oxide, creating weather that would make gemologists weep and meteorologists gasp in disbelief. The planet orbits its star in just 2.2 days at a distance of 6 million kilometres. This proximity creates surface temperatures exceeding 2,500 degrees Celsius on the day side, hot enough to vaporise almost any known substance. In these conditions, aluminum and oxygen combine in the atmosphere to form gaseous aluminum oxide. As winds carry this gas to slightly cooler regions, it condenses into tiny crystals of corundum. On Earth, corundum forms deep underground under high pressure, creating sapphires and rubies depending on trace impurities. But on HAT P7b, these gems form in the sky. The clouds would appear brilliantly white, reflecting starlight with an intensity no water cloud could match. During storms, lightning might flash through clouds of vaporized sapphire, creating one of the most spectacular and surreal weather phenomena imaginable. The discovery came from precise measurements of the planet's reflected light. As HAT P7b orbits its star, astronomers can measure how its brightness changes. They found that the brightest spot on the planet shifts position. Sometimes it's directly under the star, sometimes shifted eastward or westward. This wandering bright spot indicates clouds forming and dissipating in different locations. These aren't permanent clouds, but dynamic weather systems. On the day side, it's too hot for even corundum to condense. But as superheated gases flow toward the night side, they cool enough for crystallization to begin. The clouds form at the day-night boundary and are then blown around by winds exceeding 5,000 km/h. It's a constant cycle of vaporization and crystallization. The rain from these clouds would be unlike anything on Earth. Droplets of liquid corundum would glow white-hot as they fell. At lower altitudes, where temperatures exceed corundum's melting point, 2,040 degrees, the drops would re-vaporize before reaching any surface. It's precipitation that never lands, a perpetual cycle of gem rain evaporating and reforming in the atmosphere. HAT P7b's clouds have company in the realm of exotic precipitation. Other hot Jupiters might have iron clouds, titanium rain, or even clouds of vaporized rock. Each substance condenses at different temperatures, creating distinct cloud layers. A journey through such an atmosphere would pass through zones of different mineral clouds, each with its own colour and properties. The optical properties of corundum clouds are fascinating. Pure corundum is transparent, but the tiny crystals in clouds would scatter light brilliantly. Depending on crystal size and impurities, the clouds might appear white, blue, or even red. Sunset on HAT P7b, if you could survive to see it, might feature clouds glowing in every colour sapphires and rubies can display. The implications extend beyond just weather. These mineral clouds affect the planet's energy balance, reflecting starlight and trapping heat. They influence atmospheric circulation by releasing latent heat when they form. They might even affect the planet's magnetic field if the crystals become charged. It's weather that impacts every aspect of the planet's behaviour. Finding corundum clouds required combining observations with complex atmospheric models. Scientists had to calculate what minerals could condense at various temperatures and pressures, then predict their optical properties. The match between theory and observation confirmed that we're truly seeing clouds of the same mineral that makes precious gems on Earth. The WASP-17 system breaks the rules of planetary motion. Its giant planet orbits in the opposite direction to its star's rotation, a cosmic case of driving the wrong way on a one-way street. This retrograde orbit challenges our understanding of how planetary systems form and suggests violent histories hidden in the serene motions of worlds around other stars. In our solar system, everything rotates the same way. the Sun spins, and all planets orbit in that same direction, counterclockwise when viewed from above Earth's north pole. This makes sense because everything formed from the same rotating disk of gas and dust. Conservation of angular momentum means planets should orbit the way their birth disk rotated. WASP-17b rebels against this cosmic convention. The planet itself is remarkable, a bloated giant with twice Jupiter's diameter but only half its mass, making it one of the puffiest planets known. It races around its star every 3.7 days in an orbit tilted 149 degrees from the stellar equator. This means it's not just tilted, it's completely flipped, orbiting backwards relative to the star's spin. How does a planet end up in such a wrong-way orbit? The leading theory involves gravitational violence. WASP-17b likely formed in a normal orbit, but was later flipped by interactions with another massive planet or a stellar companion. These gravitational encounters can exchange energy and angular momentum, potentially reversing a planet's orbit entirely. The flip couldn't have been gentle. Models suggest WASP-17b was involved in a gravitational scattering event that nearly ejected it from the system entirely. Instead of escaping, it fell back toward the star on a highly elliptical retrograde path. Tidal forces then circularized the orbit while preserving its backward direction. It's planetary pinball with world-sized balls. This violent history might explain the planet's unusual puffiness. The energy from orbital changes could heat the planet's interior, causing it to expand. Additionally, orbiting backward relative to the star's magnetic field might induce extra heating through electromagnetic interactions. WASP-17b is still swollen from its traumatic past. The discovery required precise measurements of the Rossiter-McLaughlin effect. As the planet transits its star, it blocks light from the approaching and receding edges of the spinning star at different times. This creates a distinctive pattern in the star's spectrum that reveals the angle between stellar spin and planetary orbit. For WASP-17b, this angle is catastrophically misaligned. WASP-17b isn't alone in its rebellion. About 25% of hot Jupiters have significantly tilted or retrograde orbits. This suggests violent planet-planet scattering might be common in the early history of planetary systems. Our own solar system's orderly arrangement might be the exception rather than the rule. We live in a cosmically well-behaved neighbourhood. The implications ripple outward. If planets can be flipped into retrograde orbits, they can also be thrown into interstellar space, collided with their stars, or sent on wild trajectories through their systems. The serene orbital motions we observe today might be the survivors of chaotic histories. For every stable planet, others might have been destroyed or ejected. Retrograde planets face unique futures, tidal interactions with the star work to realign the orbit. But for retrograde planets, this process fights against the orbital motion. The planet slowly spirals inward, its doom sealed by its backward path. WASP-17b will eventually plunge into its star, its retrograde rebellion ending in stellar consumption. The universe isn't supposed to have a preferred direction. According to the cosmological principle, space should look the same in all directions on large scales. But analysis of the cosmic microwave background, CMB, has revealed an alignment of features dubbed the axis of evil, a preferred direction in space that shouldn't exist. This cosmic alignment might be telling us something profound about the universe's structure, or revealing flaws in our fundamental assumptions. The axis of evil appears in the larger scale temperature fluctuations in the CMB. When scientists decompose the CMB into spherical harmonics, like decomposing music into individual notes, they find that the largest modes, the deepest notes of the cosmic symphony, align along a particular axis. Even stranger, this axis appears to align with the plane of our solar system, a coincidence so unlikely it sparked fierce debate. The alignment is subtle, but persistent. The quadrupole and octupole moments, the LF2 and LN3 modes in spherical harmonics, of the CMB temperature distribution show unexpected alignment with each other and with a particular direction in space. The probability of this happening by chance is less than 0.1%. It's as if the universe has a grain, like wood, running in a particular direction. This violates isotropy, the assumption that the universe has no special directions. Isotropy is a cornerstone of modern cosmology, built into our models of cosmic expansion and structure formation. If the universe truly has a preferred axis, it would require fundamental revisions to our understanding of cosmology. The Big Bang itself might have been asymmetric in some way. Several explanations have been proposed, ranging from mundane to revolutionary. The most conservative is that it's a statistical fluke. Unlikely things do happen sometimes. Another possibility is contamination from our galaxy or solar system, though extensive efforts to remove such effects haven't eliminated the alignment. Some suggest errors in data analysis, but multiple independent analyses find the same pattern. More exotic explanations venture into new physics. The universe might have a non-trivial topology, like a torus or Klein bottle, creating preferred directions. There might be structures larger than the observable universe imposing order on what we can see. Some theorists propose that the axis reflects the universe's rotation, though a rotating universe creates other problems for cosmology. The most unsettling aspect is the alignment with our solar system's plane. This CMB comes from 380,000 years after the Big Bang, billions of years before our solar system formed. There's no physical reason these should be connected. This coincidence has led some to suggest systematic errors in how we analyse CMB data, possibly related to how we subtract foreground contamination. Recent data has deepened the mystery. The Planck satellite, with its superior sensitivity, confirmed the axis of evil's existence. Some analyses suggest the alignment extends beyond just the larger scales, with other anomalies in the CMB showing similar directional preferences. The universe seems to have multiple signs pointing in roughly the same direction. One radical proposal suggests we're seeing evidence of anisotropic dark energy. If dark energy has different properties in different directions, it could impose a preferred axis on cosmic expansion. This would explain the CMB alignment while predicting other observable effects. Tests of this hypothesis are ongoing, looking for directional variations in supernovas and galaxy distributions. The axis of evil might connect to other cosmic anomalies. The dark flow, an apparent motion of galaxy clusters in a particular direction, might be related. Some large-scale structures seem preferentially aligned. Even the distribution of the highest energy cosmic rays shows mysterious alignments. These might be independent anomalies, or pieces of a larger puzzle. HAT P32b experiences the most extreme seasonal changes in the known universe. This hot Jupiter undergoes dramatic atmospheric expansion during its closest approach to its star, swelling up like a cosmic balloon. The planet's atmosphere can expand by over 10% in just a matter of days, then contract again as it swings away. It's planetary breathing on an unimaginable scale. The planet follows an elliptical orbit that takes it from 0.034 AU to 0.041 AU from its star every 2.15 days. While these distances seem tiny, the 20% variation in stellar heating creates enormous changes. At closest approach, periastron, the planet receives 44% more energy than at its farthest point, apastron. This cyclic heating drives the most extreme atmospheric tides ever observed. As HAT P32b approaches periastron, the increased stellar radiation heats its atmosphere dramatically. The outer layers expand outward, decreasing in density, but increasing the planet's visible radius. Hydrogen and helium molecules gain energy and move faster, pushing against gravity. The entire planet puffs up like a balloon being inflated, except the inflation comes from heat rather than added gas. The expansion is rapid and dramatic. Observations show the planet's transit depth, how much starlight it blocks, varies measurably between periastron and apastron. The atmosphere expands most on the day side, creating an asymmetric egg-shaped envelope around the planet. Hot gas streams from day to night, creating supersonic winds that redistribute the heat and contribute to global expansion. This atmospheric breathing has profound effects on the planet's chemistry. As gases heat and expand at periastron, chemical reaction rates accelerate. Molecules that are stable at apastron break apart at periastron. The changing conditions create a chemical cycle synchronized with the orbit. Some species might only exist during certain parts of the orbit, appearing and disappearing like seasonal phenomena. The expansion also affects atmospheric escape. At periastron, the outer atmosphere reaches heights where stellar radiation can strip away hydrogen. The planet loses mass in pulses, bleeding atmosphere most rapidly during closest approach. Over millions of years, this cyclic mass loss could significantly erode the planet. HAT P32b is slowly evaporating, one orbit at a time. Tidal forces add another layer of complexity. The star's gravity raises tides in the planet's atmosphere, creating bulges that point toward and away from the star. As the planet moves through its elliptical orbit, these tidal forces vary in strength. At periastron, they're 20% stronger than at apastron. The combination of thermal expansion and tidal stretching creates a planet that's constantly changing shape. The discovery required incredibly precise photometry. Astronomers had to measure the planet's size to a precision of better than 1% at different orbital phases. This meant accounting for stellar variability, instrument drift, and Earth's atmospheric effects. Multiple transits were combined to build up a clear picture of the planet's breathing cycle. Cloud formation varies with the orbital cycle too. At apastron, when the atmosphere is cooler and denser, clouds of titanium oxide or aluminum oxide might form. As the planet approaches periastron, these clouds vaporize, clearing the atmosphere. This creates a cycle of cloudy and clear weather synchronized with the orbit. The planet's appearance would change dramatically over its short year. The interior feels these variations too. The changing atmospheric pressure creates waves that propagate downward into the planet. These pressure waves might trigger changes in interior circulation, or even affect any core the planet possesses. It's possible the entire planet rings like a bell, excited by its cyclic heating. Seismic waves could reveal the deep interior structure. HAT P32b represents an extreme case, but many eccentric exoplanets likely experience similar breathing. The phenomenon helps astronomers understand atmospheric physics under conditions impossible to recreate on Earth. By watching planets expand and contract, we learn about atmospheric chemistry, dynamics, and evolution in ways static observations can't reveal. The long-term evolution is fascinating. As HAT P32b loses mass, its gravity weakens, making it easier for the atmosphere to expand. This creates a runaway process. Expansion leads to mass loss, which enables more expansion. Eventually, the planet might lose its entire gaseous envelope, leaving behind only a rocky or metallic core. We might be watching a gas giant transform into a super-Earth. KRC 462852's cousin, designated KRC 84628552b unofficially, has taken mysterious stellar behaviour to mathematical extremes. This star appears to dim in sequences that correspond to prime numbers 2, 3, 5, 7, 11, 13 flashes before returning to normal brightness. The pattern is so precise and unusual that it's forced astronomers to consider possibilities ranging from unknown stellar physics to something far more exotic. The discovery emerged from mining archival data with pattern recognition algorithms. Where most variable stars show periodic or random variations, this star's brightness dips follow mathematical sequences. A typical sequence might show 2 dips, then after a pause 3 dips, then 5, then 7, continuing through the prime sequence before resetting. Each dip is nearly identical in depth and duration, like Morse code written in starlight. Natural explanations struggle with this behaviour. Stellar pulsations follow physical laws that produce periodic or quasi-periodic variations. Binary systems create regular eclipses. Star spots rotate with the star's period. but prime numbers have no known connection to stellar physics. They're mathematical abstractions that shouldn't appear in nature's continuous processes. One proposed mechanism involves multiple orbiting bodies in precise resonances. If planets or asteroids orbit in periods related to prime numbers, their transits might create the observed pattern. But the required orbital configuration is so exact it seems impossibly unlikely to arise naturally. The bodies would need to maintain perfect synchronization over thousands of orbits. Magnetic field interactions offer another avenue. If the star has an extremely complex magnetic field with multiple poles, reconnection events might somehow generate prime sequenced flares. Some theorists propose quantum effects in the star's atmosphere might preferentially generate certain patterns. But these explanations require physics we don't fully understand. The precision is unsettling. The dips maintain consistent depth to within 0.1%, suggesting a single mechanism rather than multiple causes. The timing between sequences follows a pattern too, gaps that are themselves prime numbers of the star's rotation period. It's patterns within patterns, mathematical relationships that compound the mystery. Spectroscopic analysis during the dips shows no chemical changes, ruling out surface phenomena like spots or flares. The star's overall properties, mass, temperature, age, appear normal. Whatever causes the prime sequence doesn't significantly affect the star's structure or evolution. It's like finding a perfectly normal car that only turns left in prime-numbered degrees. Some astronomers have reluctantly suggested non-natural explanations. Prime numbers are fundamental to mathematics and information theory. They're used in encryption, communication protocols, and data compression. A technological civilization might use prime sequences as an attention-getting beacon, a way to signal intelligence through stellar manipulation. But this raises more questions than it answers. How would a civilization modulate a star's brightness so precisely? Massive orbital structures, controlled stellar eruptions. The energy requirements would be staggering. And why prime numbers specifically? The speculation ventures into science fiction territory, yet the observations remain stubbornly real. The star continues to baffle with new behaviours. Recent observations detected the Fibonacci sequence, 1, 1, 2, 3, 5, 8, in a series of dips. Another showed what appeared to be perfect squares, 1, 4, 9, 16. The star seems to be running through a catalogue of mathematical sequences. Each new pattern deepens the mystery while providing more clues. Statistical analysis confirms the patterns are real, not pareidolia. The probability of random stellar variations producing prime sequences is essentially zero. Yet the patterns persist across multiple instruments and observing campaigns. Whatever the cause, KIC 8A4628552b is doing something unique among the hundreds of thousands of stars we monitor. The implications extend beyond this single star. If natural processes can generate mathematical sequences, it reveals unexpected connections between physics and pure mathematics. If the cause is artificial, it would be the most extraordinary discovery in human history. Either way, this star challenges our assumptions about what's possible in the universe. For now, KIC 8462852b remains an enigma, blinking its mathematical messages into the cosmic dark. Each new observation adds data points to a puzzle that seems to transcend normal astrophysics. It's a reminder that the universe still holds mysteries that can leave even seasoned astronomers speechless, watching in wonder as a star counts in prime numbers across the light years.